Hey, y'all. Hope everybody can see me. Can everybody see me and everybody hear me? Yes or no? I'll wait for people in the chat to let me know if you can see me and hear me. I forgot YouTube always mirrors my image. Boy, that makes it frustrating. Yes, good. Okay. Everything sound okay? Hopefully. I keep doing the new way of doing the live streams, and it mucks me up because I'm so used to seeing me not mirrored, and now YouTube mirrors me, which makes it easier to move back and forth, but it makes it harder for me now because I'm so used to the other way. Okay, I'm getting updates, and I have to get updates. I hate to tell you this. I need my phone more than ever right now, and I'll tell you why in just a second. Okay. If you've wondered, if you are my Patreon member, you know exactly why I have not been around recently. If you are someone who just sees me on YouTube, you may be wondering and scratching your head, why in the world have I not been doing forecasts for the past couple weeks? A close family member of mine is in the hospital right now with COVID, and he's not doing very well. And I'm not going to give the details out here in the open. My Patreon family knows a bit more detail, but and if you are a Patreon member, please, keep it a little bit quiet. But it scared me to death, and I've been on call, and I've been trying to give as best care as I can, because he's not he's not local to me, and it doesn't even matter because I can't even go into the COVID wing of the hospital, even if I were where he is. But he has a lot of complications, and he's older, and so it makes it very painful. So I've been on pins and needles, and I've not been able to either muster enough, calm collectedness to be able to do a rational forecast. And also just because I've been on the phone constantly, working out situations and trying to give him the best care I can. So that is why I do plan to do a forecast here soon. As you can tell, I mean, obviously I'm doing this class, so I'm getting a little bit better because he's getting a little bit better, but he's still very sick. So please bear with me if you are on YouTube and you have been starving. I've gotten a few comments from people saying, I'm starving for a new forecast. When are you going to do one? Well, this is why I haven't done one, and it's why I haven't been active in the comment boards either. So I do apologize to all of you. So hopefully that will end soon. Thank you all for tuning in. I see, thank you, prayers. I appreciate that. Hi from England. Thank you, Husky. I appreciate that. Yeah, thanks, Mandy, all of you guys. Andy, I appreciate it so much. Yes, we need it. I need space. No worries, my thoughts to you. Thank you. But yeah, that's why I have not been on Twitter either. I need space from Twitter. If you've wondered why I've been pretty quiet there as well. Life catches up to all of us, doesn't it? So on that note, this is the title slide from the last mini course I did. And so if you see your name as a mini course patron, oops, I have to do this now. See, I'm getting used to the other way. If you see your name as a mini course patron, this is from 2 months ago. This is literally from the beginning of December. If you don't see your name up here, it's because I haven't had a chance to update it, and I apologize. But like I said, it's been a nightmare for my family. Again, the same thing. I've got a few people I have added to the list of VIPs, and they may not be on the list. So I do apologize if you please don't be upset with me. I promise to get it updated by next time. But this is now the part 2 of the solar cycle and essentially the Breathing Heliosphere class. And thanks to everyone here, not only am I able to present this class, but this used to be a class that was only 1 part. It's now a 2-part class. Because I've had to add some stuff. I've had to add some stuff about the new solar cycle, where we are. I've even updated it more recently. Scott McIntosh was nice enough to give me a couple more plots from some stuff that I'm not even sure is completely published yet. Some of it is, but we keep updating things, of course, as time goes on. And so I'll show some comparisons and some of this fits and starts that our solar cycle 25 is doing. That's very frustrating to us all. But, welcome to being involved with solar physics. The sun never seems to cooperate like we want it to. Thanks, Nick. I appreciate that. I appreciate seeing you giving me positive vibes, and That's so kind. I see so many like prayers and strengths and things, and I will definitely go over the chat. I see lots of little paragraphs, which I'm not going to be able to read right now. But I will definitely go over all of the comments and read every single one of them. So thank you for putting them up there. And I really appreciate it. Okay. Yes, fits and starts with the sun. And so we will get into that. Now, usually what I do in these mini courses is that I will take a little bit of time and I'll review what I did in the past. I'm a little hesitant to review too much right now. I mean, I could go back through it, but the problem is, if I do that, is I've got like something like 30 charts I want to get through. So I don't really want to do too much review. Where we left off last time, if you guys recall, is where we were actually talking a bit. We were just beginning to get into we were just about to get into the solar cycle. But what we were mainly talking about, and I'm just kind of pulling off to the side here, we almost left basically on this chart where we were talking about how the solar cycle has all these massive variability over very long time scales. If you can see, this chart goes from 1000 AD up to 2000. So this is 1,000 years worth of solar cycle activity data. Of course, only up until recently, where you see the pink lines and stuff over here, do you start seeing where, all the extra lines, where you start seeing more modern data with, actually direct data. The rest of it is proxy data through ice cores and cosmic ray and isotopes and things like that to be able to extend our observations back. But as you can see, these lines, of course, show lots of ups and downs. And that's not the 11-year cycle. These are long periodicities. These are some of the pseudo-cycles that help modulate the solar cycle over time. And so we have lots of things like the Oort minimum, the Wolf minimum, the Sporer minimum, the Dalton minimum. We've had lots of grand solar minimums in our past. So the fact that we're kind of in a grand solar minimum now should not scare anyone. As a matter of fact, this grand solar minimum is kind of a dud, to be honest. And if McIntosh's team at NCAR and UCAR are correct, then it's really going to be a dud, because they believe solar cycle 25 might take off like a rocket. And we've seen some evidence of that, and we'll get into that in a minute. So anybody who is a grand solar minimum, devotee, yes, we're in a grand solar minimum. Okay, great, you're not wrong. But the sun isn't going to go to sleep, because it doesn't look like this grand solar minimum is as deep as some of these others are. Some of these others that we've had in the past were much deeper. And yes, sunspots went away, because basically the sun's magnetic field was so weak that the solar cycle still took place, but it all took place under the surface of the sun. There wasn't enough strength for the little submarines. If you guys recall sunspots, I often call them submarines. They weren't strong enough. They weren't buoyant enough to pop through the surface of the water, so to speak, which is the sun's surface. And so they didn't pop out and show themselves to us. So all of those dynamics took place underwater, so to speak, under the surface of the sun. And so the solar dynamo kept churning and doing its thing. It was just so weak that you couldn't see any physical manifestation. And therefore, there was very little space weather. There was no sunspots. And everybody thought the sun went to sleep and that the dynamo died, and all sorts of other crazy myths that are associated with that kind of thing when you can't see physical evidence of something continuing. So, okay, grand solar minimums happen, and they happen a lot. But this grand solar minimum doesn't look like it's going to get so weak that everything is going to shrink below the surface. We are still having sunspots. We even see evidence of the solar cycle, the next solar cycle, and likely because we are already seeing evidence of the next solar. This is solar cycle 26, okay? We're already seeing evidence of that in the flows and the jets that we're seeing. So likely solar cycle 26 will have sunspots. So it's not as deep as you think, okay? But don't worry. You are correct. We are in a grand solar minimum. I don't want anybody arguing about that. Okay, so that's kind of where we left it last time. So now I'm going to focus a bit more, now that we kind of understand dynamos, and hopefully if anybody needs to, they can go and review, whoops, how many slides did I go for? They can go and review the last course where we went into solar cycle dynamos, we went into you could tell the long periodicity, we went into sunspots, how they work, that type of thing. Now we're going to get into a bit more about solar cycle 25 and what it's doing right now, and we're going to also move outward in space to how the solar dynamo and everything about the sun that you see on the surface of the sun literally moves out to the edge of our heliosphere, and how that shield, that magnetic shield that shields our entire solar system, is yet another reflection of the solar dynamo and another reflection of our sun's, our stars' periodicity and its volatility. And you'll see how it couples with the interstellar medium. And I think that's kind of neat because it explains a lot about cosmic rays. Now, I'm not going to talk about that too much, but I will get into it a little bit. Okay. So, and I'm sorry, I'm rushing through. I probably should have said thank you even more to everybody who's a VIP and who's a Patreon mini course participant. You guys are so important to me, and I appreciate it very much. I just spent so much time on talking about my family member that I didn't want to, spend too much more time and want to get into the meat of where we are. And I'm just taking a look. I'm trying to pay attention to the chat a bit more. And and by the way, I do want to thank both Jerry Ryan and Michael Richardson. You will see wrenches by their names. They are our YouTube moderators, so I appreciate them very, very much. They are VIP members. I know Michael is taking at least the first shift, so he will be. If you have any questions or anything, he's very, very savvy. He meets with me easily once a month, and when we have our steering committee meetings, and he knows a lot about pretty much everything that's going on behind the scenes. So if you have questions that I can't get to, you might be able to ask Michael, and I'm sure he will do his best to answer them, or he will relay later on. He'll relay the message to me. They also have my cell phone, so if you really, really need to get a hold of me for some reason, they have my cell phone number, so you can get to me that way if you need to. Sorry, Mike, I shouldn't have said that because now everybody's going to say, "Hey, Michael." Anyway, okay. So I just updated this. Hang on, I'll answer this one really quickly. How many CMEs have we had this month alone? Well, let's see. Like any Earth-directed CMEs, I think 1 or 2, and they've been very weak and they've hardly hit anything. We're very disappointed in the sun this month. As a matter of fact, since about late November, we've been very disappointed with the sun, and I'll talk about that in just a second. But we are still having CMEs a lot. I mean, we just had one the other day. Just there's not been a lot that have been Earth directed, and they're still pretty weak because right now the sunspots on the sun have been pretty weak, sadly. So we're kind of scratching our heads a little bit because the sun was a bit more active back in November, and then it just decided to settle down again. But that's all part of what we're dealing with right now. I mean, right now we've got this solar cycle that's driving us nuts, right? Even at the end of the solar cycle, we were scratching our heads saying, "Where are we now?" And this is because as we started moving through the solar cycle, at least not even just the end of this one, but the end of the one prior to it as well, back in 2008, we had these really insanely deviant behavior in the sun. And it was something that we had never seen before in the space age, and it got a lot of press with solar physicists. This is kind of what started the whole thing about the grand solar minimum and the sun going to sleep, and a couple people jumped the gun saying that sunspots were going to go away, and they weren't correct. They thought sunspots were going to go away after solar cycle 24, and yet we do see sunspots for solar cycle 25. But it has shown us that even solar physicists don't get it right a lot of the time. And so these dramatic changes are definitely making predictions more complicated. We'll talk about all the different predictions for solar cycle 25. It's almost hilarious. But this is science. This is the cutting edge of our frontier. So we have to be wrong half the time, right? The consensus is that we have been in this grand minimum cycle, this grand solar minimum, but it's not a new Maunder minimum. The cycles in the grand solar minimum, these cycles are typically slower, up to about 14 years in length. Cycles when they are active, like having lots of sunspots, they're shorter, but cycles that have less sunspots are longer. Okay, that's just the way it kind of averages out. During these lower cycle, and you'll see why in a minute, it's called hemispheric asymmetry is the main reason. During these lower cycles, there's lower luminosity, meaning the sun isn't as bright, and that has to do with the magnetic field strength. There are slower plasma currents beneath the sun's surface, lower magnetic field strength, just like I mentioned, that's coupled with the brightness. There's lower activity at maximum, and they are almost always manifestations of a hemispheric asymmetry. And one of the fastest ways you can see a manifestation of the hemispheric asymmetry in the sun is whether or not the solar cycle has one peak at solar maximum or two. Okay, literally, if it's one peak, then both hemispheres reach solar maximum at the same time. When you have two peaks, that means this one hemisphere reaches solar maximum before the other one does. And that has a tendency to flatten the cycles. And you'll see it has a tendency to do even more than that, but we'll get into that in a minute. So solar cycle 24 at the end of everything, and if I stand out of the way, solar cycle 24 was double peaked, right? We had the first peak in 2011 to 2012 and the second peak between 2014 and 2015. And you can see this when we did predictions, and this is a little bit old now, but I wanted to show you this because it was actually quite funny. This is how much we struggled as a solar physics field. Back when solar cycle 24, when we were trying to do predictions at the end of solar cycle, or really at the beginning of solar cycle 24, to be honest, we had a prediction. The very first prediction came out back in 2012, and this was during the deep minimum in September of 2008. So this is when the sun was really driving us nuts, because we had originally thought that the solar minimum was going to be in 2006. And when it finally went to 2008, we're like, okay, this is what our cycle prediction will be for solar cycle 24. And we thought, okay, it's going to have about, I think it was about 150 sunspots, and or maybe 125 sunspots, and the maximum was going to occur in 2012. Then when that didn't happen, when it kept being quieter and quieter, and the sun still wasn't picking up steam, in 2013 we made another prediction. We dropped the sunspot number that we thought the prediction would be, and we moved out the maximum to 2013. Okay. And then when it still didn't happen, half a year later, in 2013 and a half, right? And so July of that year, we made yet another prediction. These are consensus predictions, right? So this is when the solar physics community is literally spinning. I mean, it's like right down the toilet. April 2011, we made yet another prediction that the sunspot maximum would be in the middle of 2013 instead of the beginning of 2013. And we dropped the solar cycle, or the solar sunspot number, down to about 60. Okay, so you can see on the same scale how radically different these predictions went from 2008, when we first started making them, to 2011, when we finally came up with this one. Now, in reality, solar cycle 24, as you all know, was a low activity cycle, but really kind of matched a little bit better, at least in size, in strength. It matched the July 2009 prediction. Okay, so it was kind of in the middle somewhere. It had about 100 sunspots. I forget exactly how many, but look at it. It was double peaked, right? If you look over here at all this yellow hash, do you see the red line inside it? That's the smooth sunspot number. The yellow hash is probably the monthly number. But you notice the two peaks, right? In this case, the first peak, I believe, was the northern hemisphere, and the second peak was the southern hemisphere. So the northern hemisphere went to solar maximum first. Then the southern hemisphere did. The funny thing is that as we've gone to solar minimum, they've switched. The southern hemisphere was like the tortoise and the hare, right? Here's the hare, that's the northern hemisphere up here. And the southern hemisphere is the tortoise. Well, the hare has now gone to sleep. If you all know the fable, the hare has been snoozing. That's the northern hemisphere. It was in the lead and thought he could just take a nap. So the northern hemisphere is still taking a nap. He's still the hare sleeping under the tree. And the southern hemisphere is a tortoise that just keeps going. So now the southern hemisphere is now ahead of the northern hemisphere. And the northern hemisphere is still napping. Somebody please throw stones at the northern hemisphere of the sun and tell that stupid hare to wake up. It's losing the race. We'll get into that. But this is what we're dealing with now, okay? It's kind of the tortoise and the hare syndrome. And sadly, the solar physics community as a whole isn't used to doing predictions this way. Most of the predictions are done using a single index. Well, they use a lot of indices, but each index is only meant for a whole sun. It's not meant for the northern hemisphere and the southern hemisphere. When you get to Earth, for example, a lot of the indices, like the AA index, which is a measure of geomagnetic activity, of Earth's magnetic activity. Believe it or not, we use that as a proxy in one of our, in several of our solar models, our solar cycle models. We use AA index as a proxy for when the sun cycle is going to pick up again. But sadly, that looks at the sun as a whole. It doesn't look at the sun from one hemisphere to another. And that's one of the things that's very unique about the McIntosh et al. Work, is that they have decided to look at the sun and separate the hemispheres and look at them as almost individual entities. And then how do they couple together? And they have discovered some really interesting things that have gotten me to follow them very, very closely over the last, 5 years or so. So we'll get into that. So I don't know if anybody remembered the original prediction of SWPC, but Space Weather Prediction Center, when they first put out a prediction for solar cycle 25, it looked like this. To me, it looked like, and I always laugh at this, because to me it looks like they took this, they put it in Photoshop, they blurred it, right, pixelated it all to death, and then pasted it right there. They're like, okay, this is kind of what we think the consensus is going to be. And the reason why it was so blurry, I mean, not to make too much fun of them, but the reason why it was so blurry is because look at the nightmare they had predicting the prior cycle. Could you imagine them feeling very confident, making a really strong prediction? So this was back in April of 2019, they made this. Okay. Terrible prediction. Since then, they've done a little bit better job. So this is what the consensus is for solar cycle 25. Sadly, once again, it's using a whole sun image, right? But if you notice, look at the last two cycles. Do you see two peaks? Right. This is part of that grand solar minimum aspect. Okay. So when you see those two peaks, know that you're seeing a cycle that isn't as active as it probably could have been if the two hemispheres were in concert, right? If they were actually working together. But as for now, this is one of the predictions, and we'll talk about this far more here as we continue moving on. Okay, so let me see if anybody has any questions, any big questions I can get very quickly. Oh my gosh, could quantum consciousness have any effect on these anomalies as well? Oh, you guys are talking, you have a little sidebar here. Okay, this is cool. I enjoy Dr. McIntosh's papers on the Hale cycle terminator. Yes, he's got some really good stuff, and a lot, and some of the classic Hale papers are really important. And they talked about, hold on, they talked about, you know, Hale really was very savvy when it came to the sun. And they talked about the hemispheres, right? Because that's part of the Hale. When you look at the Hale rule, right, and Joy's law and Hale's law, it was very hemispheric. So Hale already had that concept in mind that the northern hemisphere and the southern hemisphere are coupled, but they're not one and the same. And so there was a lot of people who, I mean, a lot of people. Sorry, there are a lot of thought that went into the idea that you have to look at the hemispheres, you know, as being coupled and not, you know, not being independent necessarily, but not necessarily being singular. And a lot of people, I don't know if we forgot about that and how important that is, or if it's just because most of our solar cycle predictions originated with geomagnetic activity at Earth and the indices we've used at Earth. And when you start from that perspective, then you start looking at the sun from a whole sun perspective. You don't think about the hemispheres. And I don't know if that's really the history of how that happened. Maybe I'll look that up sometime so I can add that to some of our lessons here. But I think it's a very interesting perspective on human nature and how certain sciences are born, that certain genius, you know, ideas are lost because they may not be popular, or because at the time nobody saw the insight. Nobody had enough foresight to realize how important a thing was going to become later. To some degree, Eugene Parker went through that when he published his paper on what the solar wind was and the Parker spiral. I mean, he had to fight for a decade or more before that began to be accepted. And now, you know, he's got Parker Solar Probe named after him, and you know, has gotten many accolades for it. So anyway, it's definitely something I should look into. Okay, so recently in one of the discussions I've had with Scott, this is from his paper from 2020. He started talking about one of the predictions. I mean, his paper actually had multiple predictions in it, and I'll show you some more slides in a second. But he actually had two predictions. One of his prediction had a solar cycle maximum starting around 2024-ish. And then he also had a prediction where you could actually get a solar maximum in 2023. Okay. Now that, if you recall from this, where July 2025 is where the consensus is of solar cycle 25, just that 2-year change, that's a radical departure from what the solar physics community consensus and the official prediction from the Space Weather Prediction Center is. And we'll talk about why that happens. Before I do that, though, I want to get you a little bit familiar with the whole concept of the grand solar minimum. We've been talking about the grand solar minimum essentially for the last 4 cycles. Do you notice? Now, these aren't smooth sunspot numbers necessarily, so it's kind of hard to see the double peaks. But do you notice from cycle 21, this is clear back in the 1970s, okay? From cycle 21, 22, 23, 24, see the downward trend? Especially the last 3 cycles, 22, 23, and 24. These have been going downward from where we were before, which was a grand solar maximum, okay? And I keep getting texts. This is my dad. Oh, shoot, I just... okay. So here's, as a cycle goes down, in each subsequent cycle, you can kind of see the double peaks getting more intense, right? Look at cycle 23. You can start really seeing the double peaks. See it? And look at cycle 24. The double peaks are even more staggered, further apart, right? And the cycle is even lower. So if, in a sense, the hemispheric asymmetry over here wasn't super bad, and then you see a little bit more spreading in a single peak to a double peak, a lot more spreading from a single peak to a double peak in cycle 23, and then even more in cycle 24, they're really spread out. Cycle 25, this is Scott McIntosh's team's prediction. Look at the jump, right? He's predicting almost 250 sunspots for this cycle. And again, look, this is his fast growing cycle. If you look straight up, you'll see it's and I can't draw my finger very well up there, but if you follow that vertical up, you'll see it's right about 2023, if I can get my hand in the right place, is where his peak is. I'm trying to see around my light here, right there. Okay, was that 2023, 2024, somewhere mid-2023? That's where he thinks the most optimistic view of his, of his team's prediction of solar cycle 25 could be. And as of November, it really looked like he was on point, and we'll explore that more in a second. But this is the whole reason why we've been talking about the grand solar minimum downward trend. But we think that we might be past the worst of it. And now, instead of having those 2 hemispheres getting further and further apart, we think the hare is going to wake up from under the tree, and the hemispheres will start getting closer and closer together. These peaks will get closer and closer together in time, and we'll start building back up again. We will see. We will see. But you can understand, you can begin to understand the solar physics community is kind of bickering with one another, friendly, in a friendly fashion, but they're still bickering with one another. If we put this in a broader context, you can see, again, so solar cycle 19 was one of the biggest cycles we've had in ages. As a matter of fact, this is where the Carrington event came, I think, when was it? Oh, no, that was 1859, my fault. That's 1955. Sorry, solar cycle 19, there was a big event. Was that the 1972? No, that was there was a 1960 something. There was a big event in cycle 19, and I can't remember which one it was. It escapes me at the moment. But if you notice, there really isn't much of a there's definitely not the double peak here. This was the largest cycle that we've had in easily the last 100 years or so. Then we dropped down to cycle 20, which was a little bit of an anomaly, and it was kind of spread out. And then we started this grand solar minimum phase. Okay, cycle 25, if you look over there, the only cycle that matches cycle 25, that exceeds cycle 25, is cycle 19. So this is why the amateur radio community is really excited, because some of them remember cycle 19. And I mean, you could talk around the world on 5 watts, which is outrageous. Now you can't even talk around the world on 5,000 watts. I'm just kidding. It's not true, but you get my point. It's a lot harder to get radio propagation because our solar flux levels are so low, because our cycles have been so small. Look at the difference between cycle 24 and cycle 19, for example, right? Huge difference. So if cycle 25 ends up popping back up here, this will be fantastic for amateur radio operators. Of course, this isn't going to be good for Starlink, for example. It isn't going to be good for the health and safety of satellites. It isn't going to be good for ADS-B, that's now mandated as a GPS solution for airlines over the United States. it's not going to be good for lots of things, because suddenly space weather is going to become a much bigger factor in our daily lives, especially compared to cycle 24. Okay, so this is why I'm paying very close attention to the NCAR UCAR work to see where we're going with this, because it could literally be a paradigm shift in how we look at space weather if it ends up being a big cycle. Now, how radically different is the cycle than than other predictions? Yeah. Can you tell they're all over the place? So this is the set of predictions, as you can see, over the course of time. We've got the two red ones are the McIntosh et al. Solar cycle predictions. Like I said, he has one that's very encouraged, the one that if we hit the terminator quickly, it will be in 2023. If we don't hit the terminator quickly, it'll be closer to, excuse me, closer to what the other predictions are, but still big, okay? The only difference really is going to be the length. In the McIntosh et al., in their predictions, the only difference is really the length of the cycle, okay, to some degree, and when maximum occurs, okay? They believe that overall, if we reach the terminator like any minute now, which we almost may have, especially back in November, we really raised our eyebrows. Then we will get something where we could actually have a maximum in 2023. Meanwhile, everybody else's predictions, right? NOAA, NASA, ISIS, for example, look at the blue line down here. Look at this. Look at the difference. So instead of 250 sunspots, we may only get 120. So right now, the cycle predictions are all over the map. And sadly, that's because our sun is doing something that we have not really had a very good chance to witness. And it's this hemispheric asymmetry. And we really just don't have enough knowledge about the different pseudocycles. And we think, and McIntosh's team believes it's a sloshing about the Gleisberg cycle, which is essentially a 60 to 80-year cycle. And both hemispheres experience it. And depending upon where they are sloshing around it, meaning lagging, leading, or lagging, that makes the Schwabe cycle in the 11-year cycle lead or lag, it's hemispheric dependent. And so if one is leading a lot and the other is lagging a lot, well, then that makes the most argument between the two hemispheres. That makes the hare sleep the longest and the turtle move the fastest, and vice versa. If the one is leading only a little and one's only lagging a little, then they're both almost in sync, and so the cycle will be much stronger. And that's the part that we just don't understand yet. But that's part of the solar dynamo, and there's all sorts of reasons for the leading and lagging. And sadly, I have yet a lot to learn when it comes to this, because it's a reasonably new field, and I'm not a solar physicist. I'm a space physicist, which makes things a little bit harder for me, because I got to learn all these other different fields that I'm tangential to, but are not what I got my PhD in. Okay, so if we blow up the cycle that I'm standing in front of, this guy right here, okay, let's just take a look a little bit more closely at what we're seeing. So this is from basically 2019 all the way up to 2023, because these are the predictions, okay? So as you can see, we blow up to where we actually have this taking off near the end of November. The black line here is actually the observed sunspot number, okay? I think it's this black is the monthly smoothed. Yeah, monthly mean. The green is actual the number. So that's why it's all over the place, right? That little thin green line. Look at it way up here, for example. If I can get my hand in the right place, right there. So that was that's the actual number going off. But then you get a smooth number that's a little bit less ratty. But look at it take off. If anybody remembers back in November of last year, November and December, man, the southern hemisphere exploded with activity. It just was crazy. And we thought, oh, this is it. This has got to be the terminator. And everything jumped up, and it sure looked like it could be. And as you can see, the beginning of that McIntosh cycle, if I can scoot, I'll try to stand in a little bit in between. So the dashed line on this side, if you look at the blow up, look at it how it shoots up really fast, and look how close it is to that big jump, right? So we were really excited, thinking, okay, maybe the the solar max in 2023 and the most optimistic guess or, prediction is going to be the one. Sadly, the sun has decided right after that little, false start, kind of like went up, fooled you, and is just kind of quieted back down. So there are still these other cycles, even the mean, the red line, the solid red line, that's the Macintosh cycle that still says 250 sunspots. But its maximum is closer to where the other cycles have predicted it to be. And in fact, the green line here, which is the mean solar cycle since 1750, is just kind of an average of all solar cycles. It doesn't deviate much from that. Okay. The only difference is that it's going to be a bit higher, right? The mean solar cycle of all the cycles doesn't go quite that high in sunspot number. But then look at the difference between that and the consensus by the panel at NOAA and SWPC and all. So one way or another, I think we're going to be able to tell when the sun finally lights up. We will very easily tell very quickly after, probably this year. If you look clear down to where 2022 begins, we will probably be able to tell which prediction is going to be closer to being spot on, because they really, between all of these predictions, they really deviate quite a bit. Okay. So hopefully by the end of this year, we will know when, and all of this rattiness that we see here, that's just all over the map, a lot of the curves will fall off this map, or of course they'll change them, right? And they'll begin to get closer and closer together. But it is just a mess right now when it comes to solar cycle prediction. So tread lightly. That's all I can say. I'm not going to tell you which one is right, because I honestly don't know. But if anybody tries to sell you on one, don't buy it. Don't buy it. They're talking too fast. Okay. So before I jump into this heavy stuff, because I'm going to talk a little bit more about hemispheric asymmetry. Let me ask if there's any major questions at the moment. Do you guys have any monster questions? Oh, thanks, Joe. I appreciate that. Prayers with you. Hang on. Things are going by too quick. It's scrolling up a little bit. 2012 was another good CME, wasn't it? Yeah, it was. We also had a good one in 2017 as well. Is the delta between the hemispheres, the amount of asymmetry, an indicator of the strength or duration of the cycle? Yes, Chris, it is. It exactly is. And we'll talk even more about that. It even affects cosmic rays. So when the two hemispheres align, okay, when the two hemispheres want to reach solar maximum at the same time, obviously they kind of think of them as almost think of them as like two separate mini cycles. And so what you do with these two separate cycles is that you overlap them. And if they overlap in time, then obviously you add them and they become a much taller, thinner cycle. But if so if I put my hands, right? So if I take, this is one cycle going up and then down, right? Let's say if this is sunspot number, so my hand goes up and then down. And if that's one hemisphere and the other hemisphere is just like it, and they line up like this, then you add them and they're almost twice as tall and just as thin, right? They line up kind of like that. But if I have the two hemisphere cycles up and down, but they only do this, then if I try to overlap them, they don't overlap very well. And what happens is that you get a line that goes like this, it goes down, and then it goes like this again. See the double hump? So what that does is it not only does it make the cycle not as tall, right? Not as high in sunspot number. It's lower in sunspot number, but it also makes it wider overall. You get something that's almost twice as long, right? It's not quite, it's never twice as long, but you can go from something like 9 years all the way up to 14. Right? Because it takes a lot longer to have one hemisphere peak and then the other hemisphere peak. But that means the solar activity isn't quite as big, but it lasts longer. Does that make sense? I hope that makes sense. I hope that helps. Let me know if that makes sense, Chris. That was something new I just did. It's a new cycle we haven't witnessed. Oh, I'm Mike McIntosh. I'm missing your point. You guys, I think you're in a conversation with someone. Tamitha, have you been working out? No. I've been working in. It's COVID, so I'm stuck here. Thank you, though. No, I was a swimmer when I was young, so I have muscle tone from way back. let's see, just missed 2017 just missed Earth and hit Mars. Yes, it did. Yes, I know. It was amazing. It was the biggest radiation storm during that period that Curiosity rover had ever seen. Right. Yeah, Simplio, you're correct. When we'll talk about the solar flux a little bit. How is the Earth-facing solar quiet related to this? Earth-facing solar quiet. What do you mean? Are you talking about the solar quiet index, or are you talking about solar quiet just that we haven't had any Earth-directed solar storms? Solar quiet, that's just something that comes from the solar wind hitting us all the time. The currents don't change all that much based on that, and it's diurnal. Red and blue spots next to each other, what's that called? When you're talking about the magnetograms, when you have red and blue spots, well, the colors, of course, are just the direction of the magnetic field. They're color-coded for scientists to help us see better. And that's just polarity reversal, right? You have two, and you can have what's called, when those two colors mix and oftentimes cause a solar flare, that reconnection, that's what happens. It's called flux cancellation. There's all sorts of things when you see one spot of a different color rise above, rise into a spot of a different color. We often call that flux emergence. You can actually just call it flux emergence. That's just when a submarine is rising to the surface, right? These magnetic submarines. Okay. And so is the sun going to sleep or going to blow up? Neither. The sun is slowly waking up. Okay, Chris, good. I'm so glad. It makes perfect sense. Excellent. Thanks, guys. I appreciate that. Have you worked with any of the SpaceX Starlink crew to know how much interference could take place on a normal cycle to its communications? No, not yet. I'd love to. I don't know if I'll ever work directly with SpaceX Starlink people, but we will see. I think it depends upon, and I don't think it's going to be so much their comm links, because they're working at like 12.5 gigahertz, which is pretty robust to all but the largest solar flare radio bursts. Meaning the highest frequency. Sun doesn't scream that at that high pitch very often, but where they have more of a risk is actually when we have big geomagnetic storms. So big solar storm hits Earth and the Earth reacts. Because they're in low Earth orbit, what happens is that the Earth's atmosphere puffs out, and when it puffs out like that, it causes more drag on those satellites. And those satellites have these massive, I don't know if you've seen them, but they've got these massive albatross wings that are their solar panels, which means it's like big parasails or something, big parachutes. They're going to cause a lot of drag. And so these satellites, sadly, will drop in their orbit, and they'll actually assume different orbits, a lower orbit. What happens is that they'll be flying just fine. They get drag, it slows them down, and then they begin to fall. And as they fall, Kepler's laws say, okay, if you're in a lower orbit, you must move faster. And so they'll speed up. They lose that potential energy, and it turns into kinetic energy, and they speed up. So basically, the satellites are expected to be here in the sky, and they're going to be lower and advanced from where they're expected to be. And so during big geomagnetic storms, we can actually lose a lot of satellites. And considering how many SpaceX is putting up, the idea that they're going to lose a lot of these satellites, at least temporarily, is pretty serious. I think it's a real risk to them. So it's not so much a comms issue from the point of view of of their communications being able to actually get through. I think the issue is going to be a tracking issue, an ephemeris issue, and I don't know how much they've taken that into account. It will be a very interesting solar cycle, I will tell you that much. Okay, Dave, you say the EFSQ relates to, oh right, when they face the Earth, yeah. Okay, hopefully you guys are having a good conversation about this. You're talking about the solar quiet, relates to sunspots going quiet when they face Earth. Well, yes and no. I mean, but it's also, the solar quiet is something that, to be honest, when it comes to space weather effects and a lot of the indices, we actually subtract out the solar quiet because it's so noisy. It's a constant, and relatively speaking, and so I don't study the quiet effects, the quiet variability. I study the transient stuff. Do I think any of that will go away? No, not as long as we have solar wind, because a lot of that is not just generated by the solar radiance. It's also generated by the solar wind and all the coupling that occurs in that regard to help create the currents. Okay. Thank you, Whiskey. That's so nice, Whiskey Drinker. Don't look at my call sign. You'll love it too much. Yeah, let's hope not, Charles. The satellites crashing into one another, I hope not. But they are laser cross-linked, those Starlink satellites. They're cross-linked to three of their nearest neighbors. So that's 4 satellites laser cross-linked to one another. Can you see how much of a nightmare this is going to be? Yeah, so they're going to have to reassess. They're going to have to figure out where those satellites are in the sky. As each one of them falls, they're going to have to then tell those satellites where the new locations are, and they'll have to adjust their laser cross-links to be able to reacquire. No, thank you. Not engineering nightmare. Can you say engineering nightmare? Okay. So this is I think it looks like everybody understood what I was talking about. So let's get into the concept of solar cycle hemispheric variability. And if anyone has read McIntosh, the McIntosh et al. Papers, I've been teaching this for quite some time. As a matter of fact, back in 2014, hopefully I'm gonna stand on the right side. Back in 2014, Scott and et al. Really started looking at this and looking at the hemispheres very purposefully. And this is a very complicated plot. I'm sorry for that. And I will, as a matter of fact, I'll just go ahead and extend that right now. What you're looking at, and I'll try to explain the whole thing, but it's a little bit complicated. What you're looking at in the top panel is 2 cycles worth of sunspot numbers, okay? So if you can read this, if I can get, I'll stand over the actual words here for a second so you can actually see the whole plot. You're seeing from 1996 all the way to essentially 2020, okay? And this was first published in 2014, so it's been updated a few times. And the top panel this is solar cycle 23. Over here, this is solar cycle 24. And yes, we've got a ton of vertical lines. Don't worry about those quite yet. If we look at solar cycle 23, okay, you see that big, tall black line. Now, it's a little bit bumpy, right, because it's smooth, but it's all like a monthly smooth, okay? Look at the lines below it, though. There's a red and blue line. Hopefully, you guys can see that they're red and blue. Those red and blue lines are also sunspot numbers, but these are the sunspot numbers that I was just talking about, where I was talking about the hemispheres. If you could take apart the cycle, the black line is the total cycle, the sun, the whole sun. But if you could take apart each hemisphere and look at the cycle in terms of hemisphere, that is what the red and blue lines are, okay? So in this case, the red line is the northern hemisphere, and the blue line is the southern hemisphere. And this is what they were doing in time, okay? So if you look and see the 2 humps, okay, and Scott has lined the 2 humps the way he's lined them, if I can put my hands in the right place here, and then over here. You'd think that the 2 main humps are this one and then this one here. He's actually pulled them over here because of what he sees in the second panel, which we'll get to in a second, okay? But if you look at the blue and the red line, you'll notice that in the first line here, okay, this is the northern hemisphere is the red line. Notice how this first tall hump corresponds to the peak in the red line, the highest point of the red line. That was the maximum of the northern hemisphere. Remember I said it peaked first in cycle 23? Then if you go over here and you see this other peak in the blue line, okay, that peak corresponds to essentially the maximum in the southern hemisphere, right? So they were out of phase. Do you see that? They were completely out of phase, right? Tortoise and the hare, so to speak. But the hare hadn't quite gone to sleep yet, and you'll see why I say that in a second. Now, let's move down through that solar cycle minimum. That was that minimum that scared us all, where everybody couldn't make a prediction to save their lives for solar cycle 24. And here's solar cycle 24, okay? Notice how low it is, first of all, when you look at the black line. See how low it is? And if you look at the red and blue lines, right, they're really different now. It's not even, I mean, they're overlapping, but nothing like overlapping here. They're way out of sync. In fact, again, if you look at the red line, you can see that's the northern hemisphere, and it peaks way early, right? The blue line, the southern hemisphere, doesn't peak till way later. I mean, we're talking years later. Look at that. The red line peaked at, what is that? When was that? Give or take an ish, around 2012-ish, right? Late 2011. The blue line didn't peak until 2014, almost 2015. Oh my gosh, that's years apart. This is why the solar cycle number is so low, right? The cycles were like this. The hemispheres were like this, next to each other, right? So solar cycles 23 was kind of like this, where they were kind of overlapping. And so you had a higher solar cycle number overall because the superposition meant that they were kind of close. But solar cycle 24, they spread apart even more. Okay, and that's what you got here. But look at this. Remember I talked about the tortoise and the hare, right? The red line is the hare. Is that correct? Did I do that correctly? Yeah. The red line is the hare, and the blue line is the tortoise. Okay. Notice, right, the red line, which is the hare, that's the northern hemisphere. He peaked first, right? Took a while for the tortoise to get there. Okay. But here's the funny thing. After you peak, it's still a race. So you race to solar maximum. Now, after solar maximum, you race to solar minimum. You race to get down as low as you can in number. Look what happened, guys. Here, obviously, the red line, the northern hemisphere, was getting closer and closer to solar minimum, right? He was lower, right? He was still ahead. What happened here? Whoops, if I can go to the right place. Look, what happened here? Did the hare go to sleep and the turtle keep going? Do you notice the turtle is now leading the race? The southern hemisphere is ahead. The southern hemisphere got to solar minimum first. Okay, so the hare, the red line, the northern hemisphere, is still sleeping, and the southern hemisphere's already passed through solar minimum and is ready to go in ready to go back to solar maximum again. He touched that cone and now he's racing back the other way, ready to go back to solar max. This is why the southern hemisphere right now is much more alive than the northern hemisphere. Take a look at the sun. If you see a sunspot on the solar disk, it's most likely in the southern hemisphere, not the northern hemisphere. The tortoise is now winning the race. And the northern hemisphere, the hare, is still sleeping under the tree. Is this weird that a Mother's Goose rhyme or an Aesop fable kind of thing can actually have, have relevance to the sun? I don't know where I come up with this stuff. It just, Oh, good. Jerry's here. Okay. Hey, Jerry. Good to see you. Anyway, so now I'm going to start calling it the tortoise and the hare, I guess, all the time. But this is what we're dealing with. And this is what a lot of the indices that we use when we try to do solar cycle analyses and predictions for the future, we don't take this stuff into account. We don't realize that there's all this sloshing about the mean. So the northern and southern hemispheres are constantly in motion, and they don't always concert. And that's what we've been having, and that's what causes the grand solar minimums and maxima, as a matter of fact. Because on average, they're always slightly out of sync. You can imagine a grand solar maximum is when they're perfectly aligned. And you can imagine a grand solar minimum is when they're perfectly not aligned. They couldn't be further apart, right? And so you just keep sloshing back and forth between those two states. So for those of you who recognize the butterfly diagram, yes, this is a butterfly diagram, right? And it's all aligned. All of this stuff is aligned. This is a butterfly diagram of the magnetic field strength. And yes, it's color-coded for northern and southern hemisphere. And or rather magnetic polarity, not northern and southern hemisphere, but magnetic polarity. And the bottom is also a butterfly diagram, but it's not a butterfly diagram in terms of sunspot number. It's a butterfly diagram in terms of bright points, right? These are the plages and the bright points, because you can get just as much information out of those as you do out of the sunspots. But bright points still exist even when sunspots go away. So that's one of the nice things. Plus, they have slightly different variabilities. For those of you who need to know what a butterfly diagram is, please review my other course. I'm not going to go back to it, but part 1 talks about it in great detail. Now, if you notice, okay, so in this, and I'll explain a little bit about what a butterfly diagram is simply because I have to explain this plot a little bit. This is a plot over latitude and time, right? So this right here is the equator, and my phone is buzzing like crazy. Hold on. Let me just make sure everything's okay. Sorry, this has been my life with a family member in the hospital. Why do they have to be so talkative while I'm on a class? Okay, oh good. He's doing better. Okay. Sorry. Always something. So this is equator, okay? And up to the north is 90 degrees north latitude, and then down from 0 to 90 degrees southern latitude, okay? So you're going to see a lot of symmetry, not in colors necessarily, but you do see that, but also in pattern, okay? And if you notice, the bands come down like this and they meet at the equator. You notice that? Okay. Up above about 55 degrees latitude, sorry, my hand's not in the right place, here we go. Up above about 55 degrees latitude, that's where those little tiny dashed lines are, if you can see them. We talk about the poleward stuff. It's kind of decoupled. This stuff up here is a little bit different. And same thing in the southern hemisphere, about 55 degrees latitude, southern hemisphere. It's decoupled from what you see essentially in the what we call the equatorial bands. That's what we talk about when we talk about the butterfly diagrams. Because when sunspot numbers, it kind of looks like butterfly wings, and that you'd see one cycle, it kind of goes down like this, and then another cycle starts and it comes like this. But the magnetic polarity of the sun is really what's causing those sunspots to manifest that way. And so, again, as I've mentioned, the sunspots really are just a manifestation of the solar dynamo. They aren't the end all, they're just a symptom, right? And really what's driving all of that is what is the solar magnetic field doing underneath? And if you notice, when you look at this, we've got these big vertical lines now, and Scott's team calls them terminators, okay? Because very dramatic things happen right after the terminator is reached. The terminator is really when the bands of magnetic field, let me get my hand in the right place, the bands of magnetic field from the previous cycle finally annihilate each other and disappear. And this is at the equator. Do you notice where my finger is? Do you notice there's tiny red and tiny blue just barely fading out? Right when those two smush into each other so much that they annihilate each other and all of this flux goes away, that's when the bands above them, see, namely the red one and the blue one here, whoops, not that blue, that one and that one can take over. That's when the new cycle bands take over, the magnetic bands take over. At that point, activity shoots like a rocket really fast, okay? It's not that those bands didn't exist prior to that. You can actually see them further back, right? Okay, but activity won't take off like a rocket until the flux near the equator is gone. That's the terminator, okay? So back in cycle 23, when that happened, there was the terminator, and sure enough, you see on the sunspot number chart, whoosh, the sunspots go up like crazy. Whoops, I should say this way. I'm looking at a mirror again. The sunspots go up like crazy. Okay, and then cycle 23 continued to go, and you see the bands coming down to about here. Let me get my hand in the right place. See how they begin to annihilate each other as they get closer and closer to the equator? This is where the sunspots go down to zero, right? They go down to 0 degrees latitude. They get right down to the equator. And right here, again, that was the terminator for solar cycle 23 going into solar cycle 24. Okay, and that's when these bands could take over. Let me move my hands here this way. See, these bands. And then they take it. Notice the different polarity. The polarity reverses. Blue is now on top, red is now on bottom, right? Blue is now in the north, red is now on the bottom, whereas solar cycle 23 was the opposite, right? That's the solar magnetic field reversing. So this is when activity started again. And look, once again, look how rapidly the sunspot numbers rise. Now, granted, it didn't rise quite as high because that was a weak cycle, this last cycle. But again, whoosh, we keep watching these bands go, 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 go. And that's what we're trying to get to now. When we talk about the terminator now, what we're waiting for are these two bands here at the equator to go away. The problem is the northern hemisphere is sleeping under a tree. We can't wake it up. Get going, northern hemisphere. We want to annihilate this field and get it done with so we can start the new cycle, please. The bands for the new cycle are already here, as you can see here. See these bands? The red and blue, they're already here. They're already waiting. We know that because we're already seeing sunspots for the new cycle at high latitudes. But we can't seem to get the northern hemisphere to give us a break. Come on, Hare, wake up and finish the race. So this is the terminator that we are now waiting for. And if you look down here, especially, I'll show this one more than the other one. If you don't believe that at the terminator, the activity shoots off like a rocket, look at the bright regions, look at the bright points here. Look how much more intense they get after that terminator. Do you see that? Even in cycle 23, when we didn't have nearly as good of observations of these bright points, we didn't have SDO, for example. Look at this. I mean, you can see really the new bands coming in, and you can see the red. You see, oops, I get my hand in the right place. See how red it gets? Sadly, we didn't have a lot of the instrumentation. You can see there's a lot of gaps in our instrumentation, but you can really see it especially once we had SDO. You can see how amazingly fast things switched on after those bands were annihilated once we hit the terminator. So we know the terminator is important, right? And we thought we were going to get the terminator in spring of 2020. Boy, were we not right. But then in November, we saw a huge rise in activity. We even got some decent solar storms out of it. Solar flux went from like 69 to 100. I mean, it was like, whoa, we're at like 105. And we thought, okay, this is it. This has got to be the terminator. We're here. And then it fizzled. What happened? Did the rabbit fall asleep again? I mean, you know, I have no earthly clue, but, and even Scott and everyone, we were all scratching our heads because we really thought that was going to be it. The one thing that was kind of a holdoff was the fact that not only do you see solar flux increase like we saw, the big jump that we saw, but cosmic rays also drop down. And that was one thing that wasn't really happening very quickly, not as quickly as we would have liked. So it was kind of dicey as to whether or not we've hit the terminator. Now, one thing that Scott shared with me a while back, and I'll see if I can stand kind of out of the way. This is the bright point, kind of a blow up of the bright regions. Notice that, and again, this is the latitude. So you can see there's latitude going up to the north and going to the south. The interesting thing is that if we look at the years, Scott did this, or Scott's team did this in a really nice way. They took these years, like especially the last few years, I think from 2016. So essentially from, let me get my hand in the right place, from about here forward, okay? From 2016 to 2017, he ended up plotting, as you can see in the side panel here, he's plotting it sideways, but what he's plotting is where the density of the bright points maximize. And if you notice, most of the bright points in the early years, from like 2016, 2017, 2017, and 2018, they all maximized right really close to the equator, okay? But, and this is what the arrows are pointing, is that if you look at the really dim red line, you can see more high latitude stuff, like around 30 degrees or so. If you go across here to see 30 degrees, both in the south and in the north, those peaks were building. And so he was really excited because it isn't just our eyes. You know, sometimes these butterfly diagrams are kind of hard to read because you can't really tell, is there more stuff going on or is this just noise? But it was really showing a statistically significant increase since 2019 at high latitudes. So we're definitely, you know, everything is pointing in the right direction that we should really be at that transition now. And how has it happened in the past? Well, let me stand. Yeah, I'll stand here for now. Here are two different solar cycles. These are the ones that you saw before, cycle 23 and cycle 24. Sunspot number down, or excuse me, this is solar flux down here at the bottom. I'll try to stand out of the, you know, let me stand on this side. Sorry, probably easier on this side. I keep hitting something. So I'll be kind of partly out of the screen here. So you can see the solar flux rising. You can actually see the double peak in solar cycle 25 or solar cycle 23, and then again in solar cycle 24. You can see where the terminator is, and look how quickly that solar flux jumps. You go from really low, you know, really down about 70 or a little bit lower than that, low 60, I mean high 60s, really up fast. And in this panel, this top panel, for example, is a blow up of that region. So you can see from 1997 to 1998, you can really see it. We had solar flux sitting around 70 something. And then as soon as we hit that terminator, that red dashed line, whew, the solar flux very quickly over the course of less than a year really jumped up to, my goodness, do you see how it says 160? So it was about 150, right? But even right away, you had this peak for a short while where you actually had solar flux jump up to 120 within a month or so of terminator. And then it just kind of, you know, wiggled its way back up. And then in solar cycle 24, it was even more dramatic. Look at this. The sunspot, I mean, the solar flux, again, was right around 70. Right around 70-ish. And then, I mean, it was almost like a night and day. Right at the terminator, it jumped up to over 100. If you can look past my arm to behind me, it's the same scale. So it's over like, it's like 110. So that's how quickly, it's like literally a light switch that comes on. So if we can annihilate those two bands, whew, it'll be so fast. And as a matter of fact, they even looked at EUVI output. This was SDO Eve's 335 angstrom line. So it's the EUV, the stuff that you see in SDO, for example, the pretty colored sun. 335 is the dark blue sun, essentially. This is Eve, so it's slightly different instrument. But you notice so quickly in 2011, as soon as we hit the terminator, there was an 85% increase, and literally within 4 months. So once the terminator is reached, those bands are annihilated, the new sunspots come out like gangbusters, and that's what causes, you can literally get bands of the new high latitude sunspots like that within just a few months. So have we reached that? I think that's what I have. Yeah, have we reached the terminator for cycle 25? Well, hard to say. So here's the solar flux. Let me stand on the side. Here's the solar flux back in November, in October and November of this past year. And there's a couple, you have a smooth number and just the actual number. So there's a couple things that are laid over, right? You got a dashed line that's showing a derived solar flux from GPS measurements, and then you've got the actual the prediction from several different sources. I'm not going to go into the details of it. And then, of course, a couple other numbers here, but don't worry about those. But you can see how radically quickly from essentially October 26th up through the early November, we jumped from just like 72 or 75 clear up to over 90. And if I had plotted this a few days later, we actually jumped up to 105. So we were way up here. I should have updated my plot, and I just didn't have a chance to. So we thought, oh my goodness, that was insane. And then at the same time, the solar flux, the X-ray flux, look what the X-ray flux was doing. All of it was just riding up super fast. We went from, being below the A floor to almost being near the C floor, just in the X-ray flux. And this was all due to the massive sunspots that came out in the southern hemisphere. So we were just really excited that maybe we actually reached the terminator. The sad thing, though, was that the cosmic rays weren't really dropping so much. Now, this is ULU, and I'll zoom into it in just a second. This is ULU data, and you can see this is all of their data. So from 1965, or 7, I think. No, 1965 goes, all that is the 11-year solar cycle variation. And no, it's not correlated, it's anti-correlated. In other words, when cosmic ray number is high, that's solar minimum. When cosmic ray number is low, that's solar maximum. Our sun shields out the cosmic rays during solar max, but it lets in the cosmic rays during solar minimum. So this is a maximum, this is a minimum. This down here is a big maximum. This up here is a low minimum, right? And same on and on and on. So as you can see, as we are here, I did this plot just yesterday. Oh, get my hand in the right place. Wait, am I doing it wrong? Of course I'm doing it wrong. Because I'm on a mirror. Okay, sorry guys. So here's where we're supposed to be. I hate the fact that I'm mirrored. I get everything backwards now. So here's where we're supposed to be in 2021. See this tiny little curve down? Okay, this little curve down didn't happen until right about the end of this last year. I'll show you a couple plots. This is ULU, which is in one location, but there are multiple locations that we will look at. And it's not a precipitous drop that we wanted to see. And so that was one of the reasons why the team was saying, I don't know if we can really call this the terminator yet. Here's a blow up of ULU from 2019 all the way to the current day. Like I said, I plotted this yesterday. You can see the peak. It does look like it was maybe around May-ish of last year, right, of 2020, maybe. And then ever since then, we've been kind of going down, right? This is percent. So percent, anything up, anything above 0 is an increase in cosmic ray flux. Anything that goes down is a decrease in cosmic ray flux. But we're talking about a decrease of 1%. Day over day, it's not a huge drop. Here's another one that's a little bit more telling. This one is in Antarctica, and it actually has the lowest energy particles. So the weakest cosmic rays can penetrate to Antarctica because they're on open field lines. I won't get into the details. That'll be one of our next mini courses where I talk about how the Earth's magnetic shield shields out things. But you can see it's a little bit more dramatic. Now with the Antarctica Neutron Monitor, it looks like we may have peaked earlier, right? This is in 2019, right? They say, yeah, we maybe peaked earlier. Kind of was a little bit of a leveling off and then a sort of a peak again, which is consistent with Ulu. I have these on the same scale. So you can see, again, right around in May, you got kind of a little bit of a peak. They had a little issue with another instrument in Dome C. That's why you've got some data anomalies in here. So don't trust this data in here. They're trying to repair it, but maybe some issues. And I'm hoping this data is actually real and trustworthy. I have yet to see if they've updated this, but I think this is trustworthy. And so if so, then we're seeing maybe a 3% decrease. And we've been seeing it just since about November of last year. So if you see that right there, there's a drop. Okay, so have we hit the terminator? Maybe. But we should be seeing, you know, another kick on here as soon as possible when it comes to sunspots, new sunspots coming back out onto the sun. But that northern hemisphere is a real bugger. So like I said, poke it with a stick, do something, wake it up, because that rabbit is really getting infuriating. Okay, and I'll talk about this. Let me see. Should I do this one? Yeah, I'll do this last one, and then I'll take questions, because we'll go into the Breathing Heliosphere part of the class. So with all of this variability going on, right, and with the tortoise and the hare, I mean, the tortoise is continuing to walk, and it's a little bit easier to predict. We know where the southern hemisphere is going. It's been far more forthright in its activity. It's the northern hemisphere that's been really bugging us, because the northern hemisphere is just not doing anything. So in this particular plot, Scott's team shared with me, this is a breaking down of their solar cycle prediction. And this is what makes it so incredibly hard, and also so incredibly hard for them to even have this is why they have several predictions in a nutshell. I mean, if Scott were online, which hopefully he isn't, because he'll rip me apart later, because he's, oh, Tamitha, you said it all wrong. Hopefully not, but if so, I'll learn. But as best as I understand it, the fact that the northern hemisphere is still kind of warbling around near solar minimum, but is not completely allowing the annihilation of these bands, and we're not exactly sure what it's going to do next. There's going to be this asymmetry, this variability, this error, essentially, in when we think these two hemispheres are going to end up reaching solar maximum. Okay, and it's also why the team has made multiple predictions, with an optimistic one saying we could reach solar max in as early as 2023, or it may be as late 2024, maybe even into 2025, if it's a worst case scenario. And part of that has to do with how their model handles is basically showing the error, and what ends up being the worst case scenario if the error, if everything shoves everything toward the slowest possible maximum we could have. And so this plot, if I stand in the right place, should I stand here? I'll stand here first. Let me stand here first. So what this plot is showing is their prediction, as you can see, okay? And it rises up to about 250 sunspots, just shy of that, but it has, again, an error. The gray swath, the width, is an error, above or below. That's the uncertainty in their prediction, but the dashed line is their average. Okay, and so you can see they have a maximum that's going to be, they believe, between somewhere mid 2023. Okay. However, if you look at the bars, both here and here, both this and then this one, the issue that they have is that those bars are indicating when the hemispheres, they believe, are going to reach maximum. And as you can see, the red hemisphere, that's going to be the southern, or that's going to be, in this case, the northern hemisphere. Okay, the northern hemisphere is, and I thought he was saying the southern hemisphere, but maybe I think it is the northern hemisphere. The red is the northern hemisphere. The blue is the southern hemisphere. And boy, I hope I don't have that backwards. I'm going by his legend that's behind me. I will correct myself. I promise I will correct myself if I'm wrong. I will talk to Scott and make sure, but I'm trying to remember, again, the whole COVID thing has kind of got me messed up. Let me be careful and say this so that I don't get anybody in trouble, including myself. These are the two hemispheres. To me, it makes sense that it's the southern hemisphere that's actually going to peak first, and Scott told me that, so I was assuming that the red bar was the southern hemisphere, but I may be totally wrong. The important takeaway is this. One of the hemispheres will peak, the error is that one of the hemispheres will peak first, and then the other hemisphere has a wider swath. And I always thought it was the northern hemisphere that had the wider swath because it was so much more unpredictable right now. If the hemispheres where these two bars, the red and the blue bar, overlap, which is right here in this region, okay, which you see encompasses anything from essentially 2022 through the middle of 2023, okay? If that happens and those two hemispheres end up peaking right around the same time, then we will have a very strong cycle. However, if we get one of the hemispheres peaking by mid-2023 and the other hemisphere still hasn't, this will be a lower cycle, and the maximum of the entire cycle will occur later. And the sad part is that the model, even as good as it is showing that one of the hemispheres could peak at any time during the entire cycle. This is how little we understand about hemispheric asymmetry. And again, this isn't just a scientist saying, well, we're going to do this. This is mathematical uncertainty, right? Statistically speaking, we don't know this cycle and how the asymmetry works well enough to give us a better mathematical constraint than this. Sad, isn't it? It's the state of solar physics, guys. As far as I know, the Macintosh team is the only people that actually look at it from a mathematical perspective with decoupling the hemispheres. And it's still very, very sloshy. But I will say this. If we only have one hemisphere peaking by 2023, we will know that the peak of the cycle will be occurring later. The peak of the whole cycle will be occurring, and SWIPC and everybody else will say that it's pushed further back. And that cycle 2023, maximum and 250 sunspots or even more than that likely will not happen. And the only way that can happen is if the northern hemisphere gets in gear. So if we don't see northern hemisphere getting more sunspots here very quickly, then it's going to push that maxima further and further back. And it's going to likely mean that the hemispheres are going to stay out of sync because the southern hemisphere continues to march forward. And so there's a very good chance that the southern hemisphere will end up peaking before the northern one does. So really, all eyes should be on the northern hemisphere to see what it's doing and how rapidly it's going to advance, because that will tell us how tall is this cycle going to be, okay? So just remember that. The faster you see this northern hemisphere actually develop sunspots, the better chance we're going to have a large cycle as opposed to a low one, and the better chance we're going to have a solar cycle maximum near 2023 as opposed to 2025. Now, again, we saw a lot of activity, near the end of last year, but it's since died again. And so that was the thing that really kind of freaked us out, where we're like, even the NCAR team is going, we're not used to this. So we're all kind of holding our breath right now. And I wish we could have better, better understanding than that. But that right now is really where we are. So hopefully, the next few months will be very telling. But definitely this next year will. We will have the answers will be in by the end of this year. I guarantee it. So hopefully, and now that ends that part, because I'm going to go to the Breathing Heliosphere now. So what I'll do is I'll take a pause and I will ask how everybody's doing, if they have questions, what's going on, yada, yada, yada. What do you guys think? NASA spouts rubbish. You are not the first person to say that, Rod. Sorry for that. But I'm just trying to, I'm trying to keep it real. Remember, we're scientists, and we're academic scientists at that, right? Space weather is a very young field, and there's not a lot of scientists out there who even look at the science as anything other than academic. It's made for academics, by academics, to do academic work and research and push the frontiers forward. Nobody in that field expects the public to take any of this information and even care. So, you know, they're not pushing for operational solutions, which are the things that we actually all need. And especially the civil and commercial industry, space industry really needs it. So we've got to change that paradigm. And I'm hoping someday we will be allowed to say NASA does not spout rubbish, because there will be a part of NASA that will be operational, and NOAA that is even more operational, that's going to cater to the public side, a civilian side. And it will allow us to have more faith in where space weather is in terms of the science. But we're still young yet. So, you know, give us a little, yeah, give us a little sympathy. We're trying. Okay, let's see. Polar reversal is taking place. Yes. I thought a lot about exactly that, what you were explaining. People around me told me I was crazy. What do you mean, Kay? Kay, you were talking about a lot about what I'm explaining. That'd be interesting if you can tell me a little bit more about that. September 17th, 2020, NASA, what will solar cycle 25 look like? You were warned. What was that? What did NASA say? NASA probably just gave the SWPC consensus. They don't talk about the Macintosh stuff very much. It's making a lot of the Macintosh stuff is making a lot of waves, but it's not the consensus of the community. The NCAR team is looking at the sun in terms of more in terms of terrestrial weather. They look at things like Rossby waves. They look at things like Coriolis forces. They look at things that make the solar dynamo function, and they actually look at bodies, other bodies, planetary bodies in our solar system, like Jupiter, in so much as to understand how gas giants handle the forces that are on them, being a rotating body. The problem with our sun, of course, is that we can't see into it very easily, right? We can't see beneath the radiative zone. So even though there's a lot of other processes that are going on in the sun, some of the gas giants in our solar system can teach us a lot about where the gases are being moved, how the convection patterns work, what forces are fighting each other, and blah, blah, blah. And we can look at those planets and actually see into them and peer deeper into them than we can in our sun right now, because we just don't have the right technology to do that. So we're learning a lot, but we have to take a lot from terrestrial weather in order to make our field move forward. Is there any correlation about the size of sunspots depending upon the stage of the solar cycle? Yes and no. The issue, and I talked a little bit about this last class, the solar dynamos we're learning there are deep convection cells, there are lighter convection cells, and then there's surface convection cells. And sunspots that are different sizes, it basically couples to where they're, what part of the dynamo they're attached to. So some of the largest sunspots are the ones that go deepest, and they're controlled by the currents and the convection that is happening very deep inside our star. Other smaller sunspots actually are more, they don't go very deep. Their roots, so to speak, don't dig very deeply. And so they're more affected by the convection, the more topical convection patterns that are at the very surface of our star. And so, yes, those things can change over time because they all change over the solar cycle. So the answer is yes, and the answer is no, because it depends upon where in this, how large the sunspot is to begin with, where it's rooted. And then, of course, how much that particular convection pattern changes over the solar cycle. Certain convection patterns don't change much at all over the solar cycle. Certain patterns change dramatically. So go back, if you can, go back and look at as a matter of fact, I'll just pull it up for a second because it's in this chart set. Here's a good slide. So I won't go into this in super detail, but I stand on this side. Yeah, I'll stand on the words. So you can see just even in this thing, you can see we have the convection zones can be really deep, right? And you have certain patterns, certain circulatory patterns that occur. And a lot of this is the same kind of patterns that you see in planetary bodies because they're rotating, right? And gas giants in particular, because they differentially rotate. When you have rocky bodies like Earth, they don't differentially rotate. They're rigid rotators. But gas giants oftentimes don't rotate. in this, at each latitude, they rotate differently. Both Saturn and Jupiter exhibit a lot of that. You've got these hexagonal patterns and stuff that you can see in the polar atmosphere that have to do with the rotation, the way the rotation is occurring there, but you don't see that at the equator. You see radically different stuff. And then, of course, again, depending upon how high you are in the atmosphere, that changes what is dominating your I shouldn't say atmosphere, but how high you are in the planetary, from the center of the planet, or of the sun in this case. That will dictate what circulatory pattern what convection pattern is dominating you. So little sunspots oftentimes deal more with all this stuff up at the top, whereas the big sunspots, the larger ones, their magnetic field, the core of it is really down much more deeply inside, I won't say the radiative zone, but inside the convection zone. So there are different cells, and you can actually see on this side, you can actually see the different convection cells, and the patterns and the details of the patterns depending upon where you are in an altitude in the convection zone. So if you can see here's one that's very, very deep. See where the deep red is right there. You can see those are the big, very macro scale patterns. If you get a little bit higher in the convection zone, then the patterns thin out. They get smaller. The scale size drops. And then if you're really close to the surface, like you see here, see where the red is really close to the surface now of this convection zone. Look how striated, look how fine the patterns are. So bigger sunspots deal with this kind of convection, smaller sunspots deal with this kind of convection. And so it's a very complicated ballet, right? And we're learning a lot more about this by looking at the gas giants that are rotating in our solar system. It's hard to do this with the sun. These aren't observations, these are models. But we are beginning to realize what it is exactly that we need to look at more in depth to be able to, understand that type of thing. Hopefully that answered that question. Check the galactic field sheet, and that will affect the solar cycle. I'll talk a little bit about that, but I'm going to talk about it more from the point of view of our solar magnetic field moving out and connecting with the intergalactic field, and then cosmic rays penetrating. I'm not going to talk about any of that forcing. I'll talk about how our heliosphere is shaped as it moves through the galactic field, but I'm not going to go into a lot more detail than that. Let's see. Are hydro flares related to any part of a cycle? No, and hydro flares, a funny thing, I think that term sadly has become a less popular term, especially when stealth CMEs have kind of taken over a lot of things. Hydro flares are basically coronal mass ejections, and oftentimes coronal mass ejections that either fall back to the sun. Sometimes they escape. There's, depending upon what your definition of hydro flare is, they do or do not. But stealth CMEs are very much like that. You don't really get a flare per se, but you do get something that ejects from the sun, and whether it makes it all the way off the sun and escapes or not is a point of contention. Stealth CMEs are a class of that, where not class of hydro flares, but a class of these very weak eruptions that really don't make a CME, a flare signature at all, but they do lift off. They're almost passive in how they lift off, and they can be considered invisible. That's why we call them stealthy CMEs. They actually have caused some pretty strong geomagnetic storms at Earth as well, if they're coupled with high-speed streams, which we think may actually be part of the mechanism that causes them to erupt. High-speed wind pushes them right off the sun. I should say push. Helps lift them off, breaks some of their magnetic ties, and helps supply the energy that then gets them off the sun. And at Earth, they can be a real pain. But yeah, if you follow the community on Twitter, Nariaki Nita, who's known as Halo CME, and I are leading papers on this. Erica Palmario is also one. Ben Lynch. There's a whole bunch of us who work on stealth CMEs, and they're a real pernicious problem because of these low activity cycles. They actually can cause some real space weather impacts that are not forecasted at all by SWPC, by anybody, unless you're actually following us on Twitter. it's really kind of frustrating. And none of the automated algorithms are set up to analyze these structures and catch them as they erupt because they're so slow. So hydro flares are, yes, are a function of if you have to look at it that way, it's a function of the solar cycle because you see them far more often during the declining phase, stealth CMEs especially. And then, of course, during solar minimum. During solar maximum, you wouldn't even know if the hydro flare occurred because there's so many things. The sun is often spitting off CMEs at, eight of them a day at solar maximum. So you'd never really tell, right? How do you find a hydro flare, which really has very little signature during that period? So some of it is an observational dependence, meaning you just can't observe them. They may be going on, you just can't observe them. And some of it, of course, is that, yes, oftentimes during solar minimum, these are the only things that ever actually occur on the sun, are these very weak eruptions. So it's, yes, there is a solar cycle dependence, but it's not just do they happen or do they not happen. It's also a function of whether or not we can observe them if they are happening all the time. So, okay. I swear I'm paying. Yeah, Texas Flash, you're always a jokester. Let's see. I missed one question, something about the Maunder minimum. I missed that. So sorry, whoever put that, I only see half of it, something about another mechanism for a Maunder. So please repeat that question. I'll see if I can get to it. Can some diving comets or other celestial body absorption affect the sunspot cycle? Probably not. I mean, those are so minimal. The sun doesn't even know. Most of those comets and things are ripped apart before they even come close to hitting the sun's surface. The sun's atmospheres, as you get closer to the core of the corona, it becomes collisional anyway. So pretty much everything is ripped off. I mean, think about comets diving into Earth. A lot of these comets are really small and they don't even make it through our Earth's atmosphere, and our Earth is tiny, right? So what do you think these same kind of comets and things are going to do to the sun? Nah, sun doesn't care, to be honest. It looks beautiful though, when these sun diving comets happen, but I don't think that they have any real impact on the sun, to be honest. They're just too small. Okay. Not to mention the solar cycle is a long time in the making. I mean, we're already seeing evidence of solar cycle 26. So a tiny little transient comet that comes in for a few days when something's been 25 years in the making, I don't think it's going to affect you very much. You know what I mean? It's like a day in your life. How much does a single day in your life affect you? Unless that day is absolutely catastrophic. But if it's just an average ordinary day, right, it's really not going to be a huge thing in your life. Okay. Any other big questions? Are you going to forget about us when you hit the big time? No, of course not. Silly, you guys are my big time. Who are you kidding? Stop saying stuff like that. You guys are my world, and you always will be. So enough. Hitting the big time is great for us all. Yes, I'm taking you with me. Trust me. I'm sticking all of you in my pocket, and you are all coming with me. I promise you that. If it ever happens. Let's hope it happens. Let's hope we can make space weather a big thing. I'd love to see space weather on the evening news. Okay, there's the question. Could asynchronous northern and southern hemisphere activity have been behind the Maunder minimum? Or do we know, or do such unusually strong minimums have some of their unknown mechanisms? No, you got it. You got it, Wickstream. That's exactly right. These grand solar minimums and grand solar maximums are exactly a function of this kind of thing, that the hemispheres get in sync and out of sync. How dramatically out of sync they are and how dramatically in sync they are does dictate the grand maximums and grand minimums. Now, is it only the Gleisberg cycle that causes this? No, but the Gleisberg cycle is one of the biggest, and I think it's one of the ones that Hale talked about immensely because it's one of the strongest envelopes of solar activity that basically modulate the 11-year, what's called the Schwabe cycle, or the 22-year, depending upon your point of view, the Schwabe cycle, which is the solar cycle that we know so much. But these envelopes really are affecting the hemispheres in slightly different ways. It affects the hemispheres equally, but it affects them in different ways, and so it gets them in sync and out of sync. And yes, that's exactly what we believe is causing a lot of this stuff. So you got it. You nailed it. Okay, let's see. What other questions, guys? I'm getting ready to move on here. The reason I mentioned the galactic field sheet is because our planet is affected by our sun's field. Wait, I missed it. Our planet is affected by our sun's field sheets, and the solar cycle can be directly affected by the flip in the galactic evidence Yeah, if we were able to understand our galactic, our interplanetary, or I mean, our interstellar medium better than we do. We're just beginning to probe that. A lot of people are trying to make progress with Faraday rotation to understand the magnetic field of things. But the problem that we have is that Voyager 1 and Voyager 2 are the only ones that have actually, only probes, in situ probes, that have left our heliosphere, right? They're now in the interstellar medium. And the problem is, and I'm not even sure they're in pristine interstellar medium, and I'll talk about what that is in a minute. The problem is, when we look out at these other stars, we can see the interstellar medium, but it's called remote sensing because what it means, it's an integrated line of sight, meaning everything from where that star is or wherever we're looking, all the way up to where we are now, is being added, right? We have to see through all of that junk. That's fine when it comes to light. We can make sense of it to a great degree. Can't make sense of it when it's magnetic field, because magnetic field will point this way, and then it'll point this way, and then it'll point this way, and then it'll point this way, and it'll point this way, and it'll point this way, and all the way up to you, right? And if you keep adding vectors that point in all these different directions, eventually you just get nothing. It just ends up being nothing. So you really don't know what you might be able to get an additive number, but you won't know the overall behavior, what it actually looked like, what the field looked like at this point, or at this point, or at this point. You can't do that. All you get is a sum, right? So like if I wanted to add 10, I have a number 10, but how did I make 10? Was it 1 plus 9? Was it 2 plus 2 plus 2 plus 2 plus 2? I mean, we can't dissect all that. And so it becomes a real problem because we don't have an unambiguous solution. Another way of looking at it is, you can cast a shadow on the ground, but by looking at your shadow on the ground, can you really tell what you look like? No, you just see a shadow. There's all sorts of things that can cast that same or a very similar shadow, but it definitely does not uniquely describe you, right? I mean, I would much rather see you than look at your shadow and then try to figure out what you might look like from it. And that's the problem with remote sensing, right? It flattens everything so that we don't really get a full view of what we're looking at. And magnetic field is notoriously difficult to probe that way. And really, how our heliosphere, how our planet, right, our magnetic shield, our sun's magnetic shield, and the interstellar magnetic shield, how they all interact together. I mean, that's kind of how the dynamics of astrophysical plasmas work, is very much through their magnetic and electric fields. And yet they're the hardest things for us to see. So we've got a long way to go before we can even begin to answer how that coupling between the interstellar magnetic field and Earth's and our sun's magnetic field actually works, and how it might actually impact the dynamics of our star, or just the dynamics of our solar system, and how things penetrate. We can talk a little bit about it because of cosmic rays and energetic neutral atoms, which I'll get to here in just a moment. So let me try to button up these questions, because this is a good segue into the next section. All right, I think you're very welcome, Robert. The reason I'm a Patreon backer. Thanks so much. Yes, I will hopefully everybody will be out of the hospital and no new people will go in. Okay. I think, guys, that in the end, the result of all the vectors combined is probably 0. Well, or just some finite number. No matter what, it's not going to give us the details that we want or that we need to be able to understand the dynamics. Yeah, we don't have, right, Michael, we don't have enough data in the universal model. There's no doubt. We don't have any probes out there. We need in situ probes. We can't just look at things from a distance and expect to understand it because of that problem. Okay. Yeah, I wish we knew more about quantum entanglements, because that would definitely help us, wouldn't it? All right, so let me pull this back here, take another sip. So we will talk about our heliosphere, the shield of our solar system. As some of you have already rightly stated, we do have, we have, just like an Earth's magnetic shield, we have a solar magnetic shield. And this solar magnetic shield works, let me stand over here. The solar magnetic shield works to basically cradle and encapsulate our solar system in this bubble. this bubble of solar wind that's being emanated by our star. You can see it out here, and it's blowing out radially in all directions. Okay. Now, we'll start talking more about the terms here in a second. There's, believe it or not, there's multiple shock waves. So if you've ever looked at some of the papers on Voyager, or just some of the news articles on Voyager, you'll hear things like termination shock, bow shock, heliopause, all this kind of stuff. We'll talk a little bit about that. But basically, there's all sorts of things that have to happen before the solar wind that blows out from our star, remember it also has magnetic field in it, can actually transition out into what is the interstellar medium. Okay, there's all these standing processes that occur. They're all like pretty much in steady state. And of course, we're talking about a long way away, right? We have 93 million miles to the Earth, but the sun to Pluto is 3.67 billion miles, right? It takes more than 5 hours for sun to travel from light to travel from the sun itself to Pluto. So that's pretty crazy. The light itself is more than 5 hours old by the time it reaches Pluto. And that's pretty far. Now, the other thing that when you think about how big, the large space that we have to deal with here. So you can imagine where our solar wind ends up stopping. You have another big space before you hit a heliopause, and then another big space before you hit a bow shock that takes you directly into the pristine interstellar wind. And as Voyager and Pioneer and all these spacecraft exited these regimes, as a matter of fact, I don't even think Voyagers have passed the bow shock. They're in something that's called the heliosheath, or they're either in the heliosheath here, sorry, or they're in the interstellar sheath, where they're still not out into pristine interstellar wind. Both these regimes in here, between these blue lines, have actually been mucked with by either some kind of shock, a shock wave, like the termination shock, that affects what's going on in the heliosheath, or the bow shock, which is what's affecting what's going on in this interstellar sheath. So still to this day, Voyager, I don't think we know whether or not Voyager's is out in pristine interstellar wind, sampling unshocked plasma from way out here. But what has penetrated are galactic cosmic rays. Now, galactic cosmic rays are the energetic particles from other stars, essentially. Are there some from supernovas? Yes. Are there some from, you can think of all sorts of different types of astrophysical, phenomena and celestial bodies that can create these very energetic particles. And they come in from all over. They're all penetrating from all the way around. So we're bathing in it. Every direction you look, you see these things. They're slightly different from solar energetic particles, what we call radiation storms, mainly in their direction. They're higher energy, but they're still particles, mainly protons, okay? And we call them rays, but they're not rays. They're actually particles. And they're slightly higher energy, depending upon your point of view. Some of them are very, very high energy. But they come in from all directions. And so we can always tell the difference between galactic cosmic ray particles, protons, let's say, from solar energetic protons, right, from radiation storms, because of not just their direction, but also their energy typically. But they all are hitting us all the time. And believe it or not, our sun's magnetic shield helps shield us out from this stuff. Now, because we talked about the breathing heliosphere, and I've got to be careful, I'm going to make sure hang on a second. Let me just check really fast, because I've got to be off by 1, and I just want to make sure I'm not going to get myself in trouble. Okay, I got a lot of slides to go through. I'll try to go through fast. Because we've already talked a lot about solar cycles going in and out, right? The solar cycles getting strong or getting weak. You have to know that the shield of our sun, the shield of our star, right, as it blows out this solar wind, that solar wind at certain times, like during solar maximum, is going to be a bit stronger. The magnetic field in the solar wind is strong relative to solar minimum. The speed of that solar wind is more ordered during solar minimum, and it's shaped slightly differently. We've talked about this before when I was talking about a few courses back, when I was talking about fast wind streams And this might be a reminder of how we know this. This is Ulysses. This was one of the spacecraft that went over the poles back in the late 90s and early 2000s. And if you guys remember this being a polar plot, I've shown these before. The polar plot, basically in this case, we're showing, I think this is the speed. Is this the speed of the wind? Yeah, speed of the solar wind during solar minimum and then during solar maximum. The colors that you're seeing are the direction of the magnetic field. And if you look at it, how you do polar plots, if you look at it from, let's say, the center of the sun being 0, the longer that further out you are, that's the higher the speed. Okay, so here, as you see that you're going around, because Ulysses went from a latitude, from a very high latitude in the south, all the way up to high latitude in the north, it's actually plotting at the same time we're plotting the speed. So high speeds will be out further away from the sun, low speeds will be closer into the sun. It's just like the length of the arm that is, you know, that's how polar plots work. Again, if it confuses you, I won't take time to explain it too much. Go back to one of my other, my class when I talk about high speed and slow speed wind, and we talk about Ulysses quite a bit. So you're seeing during 1994, as it made its pass from high latitude in the south up to low latitudes, you can see that speed drop quite a bit, right? Because you went from high speed coronal hole wind and polar hole wind to low latitude equatorial slow solar wind. And the speed drops quite a bit. As you get to the equator, the magnetic field changes. That's why it goes from blue to red. And as Ulysses continues to go up now in the northern hemisphere, up to higher latitudes, once again, after you get to about 25 degrees, there goes the speed up again. So now you're hitting fast solar wind, and it stays fast all the way. So very well ordered. Magnetic field changes over the hemisphere, and the slow solar wind is confined to the low latitude bands, you know, near the equator. Solar maximum, however, yikes, what a mess. Coronal holes can be anywhere, fast solar wind can be anywhere, and overall, the magnetic field, you've lost your dipole field of the sun, so it's not ordered well at all. So you've got blue and red magnetic field, you know, in and out magnetic field, polarities are all over the place. You've got fast solar wind at any latitude, and slow solar wind pretty much at any latitude. So this was in 2000 during solar maximum, and you can see what a mess. I mean, what a difference a day makes, right? Solar minimum is when the magnetic field is very ordered by a dipole field. Solar maximum is when, sadly, the sun looks like a coronavirus. There are no pun intended, but we have no dipole field ordering it. We have a multipolar sun, and therefore it's just a total mess. Okay, and is it this one that I have yeah, I think I have the movie here. And you can watch this. Oh, poop. Hold on. Whoop, no, I don't want to change the name. Come on. Exit this. Thank you. Boy, I have to work to get this movie, don't I? What a pain in the tush. Okay. Oh, I don't want the sound. No, thank you. All right, let me get to this. I think it's about a minute into it. I want to show you. So this, I loved this animation. We'll let it play for this next 10 seconds. Hopefully good, it goes off. Okay, let me stand over here. So here's our sun, right? And what you're about to see, if I get out of the way, is that animation. There's the polar plot, okay? And here's solar wind speed. You can see 800 to 500. Oops, let me stand over here. So you're actually watching during solar minimum a beautiful ordered field, right? You've got magnetic field red and blue, and that's what the high speed is always at the poles. But as you get to solar maximum and the north and the south begin to flip, you'll see those two words, see north and south flipping. The magnetic field gets all messy, and the fast wind really just dies. You can get it anywhere. And then when it switches, when the poles reverse and get back up, you get a beautiful dipole field again. It reorders itself, but the magnetic field is flipped. So let me play it again. And I'll play it from this perspective. And this is what Ulysses taught us. Before that mission, we never knew that. But think about this in terms, this is a solar cycle. Think about it in terms of how it might affect that bubble of solar wind that we're in. So this is solar minimum, okay? This is what it looks like during solar minimum. Very well ordered magnetic field. You got a dipole field. It's very, slow solar wind at the equator, fast solar wind at the poles. Here is reaching solar maximum, okay? Now we're getting close to solar max. I mean, they're showing the north and south flip. They're trying to flip. The dipole field is gone, right? And now it goes back out to a solar minimum field again. Notice the blue is on top in the northern hemisphere. The red is on the bottom southern hemisphere. And that is what we deal with. That is the breathing to a great degree of the heliosphere. And that is what Ulysses taught us. Okay, so that's when I show you this plot. Okay, so again, this is that beautiful, pristine solar minimum stuff. This is the messy solar maximum stuff. So you can imagine as that solar wind blows out through the course of a solar cycle, you keep switching from this to this. And so that bubble of solar wind that we talked about here, that bubble of solar wind is going to be kind of breathing in and out, right? And the magnetic field is going to be changing and get very, very complicated in certain times and very, very pristine at other times, right? Especially during solar minimum, when you get that really well-ordered magnetic field and you get it very nicely formed up in the northern hemisphere and down in the southern hemisphere, it makes it very inviting because you don't have a lot of stochastic mess to try to lift through and get through. It actually makes it quite inviting for galactic cosmic rays, and we'll talk about that in a second. So just think of this orange bubble as something that's not just an egg that's stagnant, but something that's moving all the time, in and out. Here's just another way of looking at it. I often show my students this. Remember I talked about those vectors, right? The longer the vectors, the longer those arrows are. If you didn't understand what a polar plot looked like, the longer those vectors are, those arrows are, that's how strong the magnetic field is. Not strong magnetic field. That's how fast the solar wind is moving. So the shorter arrows are slower solar wind. The longer arrows are faster solar wind. And there's a huge difference between solar minimum and solar maximum, right? And again, here's another way of looking at it. And I think I can stand on this side this time. This is, again, more Ulysses data. And I've shown a plot like this before. You got the minimum, maximum, and then getting close to minimum again in the yellow. Again, the same kind of polar plots as you saw before. And of course, it does affect the sunspot number, right? And they've got it, it's nice because they've gotten it color coded. So you can see the pink was taken during this period here where we're going down from the declining phase to the solar minimum. The teal or cyan color was during the solar max of cycle 23. You can see it in cyan. And then yellow at the very end was taken during the declining phase of solar cycle 23. But it's not just the sunspot number that varies, also the current sheet tilt. And if you guys remember the current sheet, that has to do with the sun's magnetic neutral line. Again, if you look at the class that I taught on high-speed streams and how coronal holes are formed and all that kind of stuff, I talk about the current sheet and I talk about the magnetic neutral line. And the tilt of that current sheet really is dictated very much by how well formed that dipole field is. During the dipole field, when the dipole field is really well formed, let's say in the pink and in the yellow regions, you're going to have a dipole field, the current sheet tilt is very low. It's pretty flat. And I've talked about it as a sombrero. But during other periods, as you start moving towards solar maximum, that tilt of the current sheet, that sombrero, which is like this big party hat, that the current sheet kind of comes out and it comes out like in the solar wind and folds out. And I'll talk about it. We talk about it being the ballerina skirt in a prior class. I think it might even be a title of the class. I might have talked about that. But that was all when we were talking about the fast solar wind and how the heliospheric current sheet moves out and how it's formed. All of that is very much governed by the solar dynamo and governed by how much that magnetic field is a dipole field. So at solar minimum, that dipole field is flat and that current sheet is got a low tilt. As we move to solar maximum, that tilt increases. And then as the sun rotates, you can imagine that tilt does this. So it becomes like this really crazy wobbly looking thing. And that affects how it looks when you talk about the Parker spiral, and I'll show you all that. But as you can see, it's very much aligned. The tilt of the current sheet, which is this bottom panel here, is very much aligned with the solar cycle. And the tilt of the current sheet is very high during solar max. It's very low during solar min. Okay. And I guess I'll show that next. No, hang on. I'm just checking something. Let me just give you a hint because I'll jump back to it. Here is, and I'll show you a movie of it so you'll get to see. Do you guys remember the ballerina skirt, right? This is what I had taught before. Here's a picture in case you guys needed a little bit of a review. Here is the neutral line on the sun. This is the magnetic neutral line. This is basically the magnetic equator, and it's that magnetic equator that's the tilt. That causes the tilt of the current sheet. During solar minimum, this magnetic equator is pretty flat. It's pretty much like the geographic equator on the sun. But as we get closer to solar maximum, that equator tilts. Okay, tilts this way or this way. And as the sun rotates, that tilt makes it look wobbly. So as you take that current sheet out from the surface of the sun, as you blow out the solar wind, it takes that magnetic field and takes it out with it. Okay, so you get this really crazy looking ballerina skirt. This is showing how the magnetic field and the current sheet is tilted, and yet it's got the Parker spiral in it as well. So it creates this really crazy looking spiral and ballerina thing that really it's all part and parcel of how the sun's magnetic field is dragged out in the heliosphere, and it helps make our shield. And I'll show you a movie about it in a second. But you should remember a lot of this stuff from when I've gone over this before. This is not the first time I've talked about this. One thing I want to make sure, though, that this is the first time I've talked about this part. No, I got to stand on this side. Here's the sun. We're looking at it from kind of an oblique angle, okay? And what you're looking at in these spirals, actually I should do it this way because I'm not in a mirror. What you're looking at in these spirals is the spiral magnetic field lines, right? When we talked about the solar wind and the Parker spiral, how they came out. These are Parker spiral field lines. And in the equator region, remember, this is not the first time I've talked about this. I've said this many times. In the equator region, it looks very much like a pinwheel, okay? But what we hadn't really talked about is how does this Parker spiral look once you move away from the equator and you get out of the ecliptic plane and you begin to look more toward the poles? Well, because you have not magnetic field, you have plasma being shot out of the poles this way, right? The solar wind is actually being blown up. It takes those magnetic field lines and drags them out, but it drags them up a spiral. Okay? So the spirals, instead of sitting in the equator like this, begin to spiral up and around. And the closer you get to the pole, the looser those spirals become, the more straight line they become. And as you get right up to the pole, the field lines are almost straight out. Because now, instead of spinning around like this, they're spinning like this, right? I'm spinning like this. And if I'm shooting out, I'm really not doing much to that field line because it's just going straight up and it's just spinning around its axis. So as that happens, these field lines get less wound as a helix and more straight because they don't care, they just spin, right? So that's the neat thing about the Parker spiral as you move away from the pole. But that has consequences because it makes the solar wind with the magnetic field orientation look very different depending upon if you're at the equator of our sun's magnetic shield or if you're at the poles. So if you're a cosmic ray and you're looking at the Earth's magnet, or you're looking at the sun's magnetic shield, and you're thinking, how do I get in that thing? You're going to find the most interesting or the easiest path to take, aren't you? What do you think? Do you think this is very easy? Or do you think maybe this line might be a little easier? Should give you a hint where I'm going. So, and I'll put these in. So a couple astrophysicists who are also heliospheric physicists and modelers decided to kind of take a look at how the sun's magnetic field and the whole concept of the Parker spiral, especially near the poles, how it actually works and what you would anticipate and how does it couple to to our celestial field, right? Now, first of all, one thing you need to know is that the magnetic field of the sun and the axis of the sun's rotation is not really in line with the galactic center, right? So from a galactic perspective, our sun kind of wobbles and it wobbles in and out. It doesn't wobble in and out of the ecliptic plane per se, but it does wobble. And so its magnetic moment is slightly offset. And so instead of having what Parker said would have been a perfect, what I call waffle cone, which is the magnetic field spiraling, up and outward in the poles. So that's the Parker spiral kind of doing that spiraling, but spiraling up. Because the sun wobbles back and forth a little bit as it spins, it's a little bit more spaghetti. Okay, this is what Fisk kept in mind. But even if you have field line motion, what he called field line motion, because of this wobble in its state, you still get something that works very much like a waffle cone. And it's still more enticing, as you can see the funnel. Do you see this nice little funnel that comes down? That is almost like a guide for cosmic rays. And if you could imagine, right, if you're a cosmic ray, you have a choice of either going through something that looks like this near the equator, or something that wants to funnel you in like this at the poles. I don't know, to me, the choice gets pretty clear. And on top of that, let's not just talk about that. Let's also talk about the fact, if you guys recall, with the ballerina skirt, this is where slow solar wind is. It's kind of embedded in and around this ballerina skirt, this heliospheric current sheet. Above it and below it, on either side, is where you're going to find a lot of coronal hole fast solar winds. So you get a lot of solar wind stream interactions, and that's what this is. Now, I think I might have shown this plot back during that course on stream interactions on fast solar wind. I don't remember if I called it the fast solar wind, if I just called it the sources of the solar wind. But that is where a lot of the core of this is coming, because this is where we're talking about how the sun takes its influence and pushes it out to the edges of our heliosphere. And this is really the structure of the solar wind. So if we look at it from above, we're looking down onto the sun's north pole here. All these little red blobs are stream interaction regions, and they're pretty much confined to the equator. If we look at it from the side, the blue line, so you can see the sun. Okay, so the North Pole is looking down the sun here. The Southern Pole is looking up from that angle. The blue line here that wobs in and out, that is a cut through, like a straight cut through the heliospheric current sheet. Okay, so that ballerina skirt, that's what the ballerina skirt looks like on its side. And remember, fast and slow solar wind meet and cause what are called SIRs, these stream interaction regions. That's what the red is. So where you see the interface between fast and slow solar wind, you're going to find all these stream interaction regions. Okay? As you move outward toward the edge of the heliosphere, these stream interaction regions get closer and closer together. They become merged interaction regions. I did talk about that then in that course. And I'm just kind of reminding you of it, because this is the stuff that cosmic rays will see at low latitudes. They'll see all of this crazy mess. Okay? And if I show you a movie, I love this movie, it'll give you an idea of what a pain in the tush it is. Is this the right movie? Yeah, hang on. So hello. Now we'll probably play it a few times. But this is the sun, obviously, that you see behind me. And as we move out, what you're going to see are the waffle cones in red and blue, northern and southern hemispheres. And then you're also going to see the ballerina skirt, okay? And we're going to keep moving out to the edge of our heliosphere, and I'll try to navigate and tell you what we're looking at, okay? So here we go. So there's the sun moving out. And now you're seeing those are the spiral field lines. That's a Parker spiral. Hopefully you can see that at high latitudes, red and blue. And there's the ballerina skirt in purple. Okay, then that you can see the Parker spiral. So the red and blue are the waffle cones at high latitudes. That is what the magnetic field looks like. At low latitudes, you get more that current sheet, that heliospheric current sheet. Now, if we cut through it, let me get out of the way. They're going to take a plane out. Okay, so hang on a sec. Let me rewind it for just a second before we get to that point. Okay, so if you notice, before we get there, and I probably can stand, I think I can stand on the side and you guys can still see. So see the red and blue waffle cones, right? They look like nice little funnels. I always call them waffle cones. Someone's probably going to shoot me for that, but oh well. So there's that's what the magnetic field lines look like at high latitudes. In this section, you're getting this heliospheric current sheet that's got high density and all these little wavy, fast and slow wind streams, plus a magnetic field that's, changing direction, up, down, the whole time. As you get closer and closer to the edge where our termination shock is, that solar wind is going to be stood off. It's going to be pushed back upon by the galactic's interstellar wind. And so it's going to compress as you get closer and closer to the edge of the influence of our heliosphere. The reason why is that as the solar wind comes out, it may get faster and faster, but it gets weaker and weaker. And eventually that bubble can no longer stand off, that solar wind can no longer stand off the pressure of the interstellar wind pushing against it. So that's why it gets compressed here at the edge. But if you notice, the field is going up, down, right? And getting compressed in a sheet. So when you see this white sheet come out here in just a second, right? What it's seeing is a bunch of things poking through it. It's going to show you the magnetic field. When it flips over, it'll flip itself and put it right in front of the camera. And you'll see all these lines cutting through it. What they're showing is this magnetic field cutting through it in these what are called merged interaction regions. All these regions, because remember, it's like a fold of a ribbon, right? And it's cutting through the sheet, up, down, up, down, up, down. So what it's trying to show you is a cross section of that. Okay, so hopefully that makes sense. And so let me play it now, try to get out of the way. So as it plays it, there's the sheet coming out, and you're going to see a bunch of lines. Those are the merged interaction regions. I'm stopping. Those are the cuts of each one of those folds of the ribbon. Okay, but each one of these folds is actually magnetic field as well as plasma and stuff. It's all these stream interaction regions and heliospheric current sheet crossings all smashed together, really tightly packed. And look what happens. This is what the models show is the magnetic field during all of this. Yuck. Look how corpuscular it looks. I think it'll just stay like that. Good. See how corpuscular it looks? Isn't it funny that when you look at this, it almost looks like the surface of the sun again, doesn't it? So imagine the edge of that bubble almost looks exactly the way the convection cells, the granulation cells on the surface of the sun. It's just now projected to the edge of our heliosphere. But here's the trick. If you're a cosmic ray, do you think you want to try to shoot yourself through that? Because remember, you still got to pay attention to all the magnetic and electric fields that are going on. You're not really going to want to do that, right? Wouldn't you rather be funneled in? I don't know about you, but I'd rather be funneled in. So believe it or not, cosmic rays, not only do they like weak magnetic field because then they can force themselves in better, but they actually like to penetrate into our heliosphere at the poles. They don't like to come in through this mess because it makes it harder. It's harder for them to get through all that stochastic mess. So that, honestly, is what our heliosphere looks like. And how do I get back to, yeah, there we go. Okay. So, you thought that you were just going to get something very simple that looked like a bubble. And in actuality, you get something that's far more complicated than that. And that's what a lot of these a lot of these cosmic rays, these charged particles see when they see the edge of our heliosphere. Now, of course, with the solar cycle on top of all this, I'm making you drink from a fire hose or anything, but on top of all of that complexity, we also have, of course, the solar cycle variability going up and down and up and down. And as you can see, the sunspot number, well, you don't really see them, they didn't plot the numbers, but on top of the sunspot number, you also get the magnetic field intensity. Let me stand over here. The solar wind magnetic field intensity typically goes from a couple nanotesla up to about 10 or so nanotesla during solar maximum. But as you can see, as we got to where I'm standing, down near 2010, that was at the end of cycle 23, we had magnetic field numbers that were almost zero. So our magnetic field was into the solar wind at 1 AU at Earth was incredibly weak, right? So it was the weakest we had seen at the space age, and the solar wind itself was the weakest. Here's another polar plot showing back in 1992 through 1998. That's the green line showing the dynamic pressure. Wasn't too bad, but when we got up to 2008, which was when we had the solar cycle minimum that was really, really low, we had dynamic pressure that was down at 1 nanopascal, almost 5 times less. So it was very, very weak pressure pushing out, very, very weak magnetic field pushing out. And what did we have to contend with was all of this junk, right? All of the cosmic rays coming from all of these sources. I mean, even Alpha Centauri, the nearest star system, is only about less than 2 light years away. We have the Oort cloud. We have lots of other sources of galactic cosmic rays coming in to our heliosphere. And yet our heliosphere, if I get over on this side, was the weakest we had seen it ever. And so what did that mean when it came to cosmic rays? Well, I'll talk about that in just, I'll get to that in a second. Let me, I probably should have put this plot in a slightly different place, but before we get there, let me explain a little bit more about this whole dynamic stuff. This is what I was talking about when I first put up the plot of the heliosphere. I was talking a little bit more about how the heliosphere terminates. And that's what I'm going to go into now. So here's the bubble, right? This is the bubble. This is the egg that we talked about that breathes, this green bubble, okay? Now, why do we have to have 2 shocks? Why does there have to be 2 of them? Why does there have to be a termination shock and a bow shock? I get that question actually quite a bit. And the reason why is because we have 2 different winds blowing on each other. We have the solar wind blowing out from our sun, and we have the interstellar wind blowing in from the galactic center, okay, or wherever it's coming from. Forgive me if I got that wrong, but I would imagine it's from the galactic center. But maybe it's just from the spiral arms coming through. And starting in our little solar system, that solar wind, as it continues to blow out, it no longer can stand off the pressure that's coming and pushing on it. Whoops, I'm doing it the wrong way. Pushing on it this way. Sorry, that mirror again, that mirrored image. So the galactic wind is pushing on it this way, and it can no longer stand off, but it is still moving out supersonically, faster than the speed of sound in space. It's a special kind of speed of sound. It's not acoustic speed of sound. It's a different kind of sound wave. It's electromagnetic sound wave, but nonetheless, it's faster than it's what we call supersonic, and it has to stop. And the problem is, because it's supersonic, it doesn't have a chance in its current state. It's moving too fast to actually move out of the way before this wind comes and smashes it. And naturally, how nature fixes that is it creates a shock wave. And what that shock wave does is it slows it takes energy out of the speed of those particles of that solar wind and turns it into heat. Okay, so at this termination shock where you see the green, okay, and the green temperature is lower than the red. This is all in temperature color bar. Okay, it slows that solar wind down right at that bubble and heats it like fire, heats it up quite a bit, so that it can divert. You see the flow lines? It can divert all that solar wind down what we call the heliotail. Remember the Earth's magnetic tail? I talked about it. Same thing. The sun has a magnetic tail. Can you believe it? Oh my goodness. So all of that hot stuff that you see in red is now subsonic, and it can be bent and flowed out of the way. So this big solar wind, or this big interstellar wind, can now slam into it and have a hope of getting by. Okay, so that's why our heliosphere actually looks like a bubble to some degree, but then there's all of this hot tail that goes around it. Okay. Once you get to the edge of it, where that hot tail begins to cool down, that's the heliopause. It's not pristine solar wind from our sun, right? It's been shocked and changed, but now it's beginning to flow around. It's flowing back behind it so that this interstellar stuff can hit. The interstellar stuff sees not just the bubble of solar wind, it sees this whole heliotail, and it goes, whoa, look at this big obstacle. My God, it's a big baseball coming through the air. So it has to be shocked as well. That's the bow shock for the interstellar wind that's blowing in this way. See the flow? Right? So that you get this bow shock, and inside that, what it's doing is it's heating. Once again, heating it, okay, not so much, but heating it. It heats that flow and then allows that flow to move around this obstacle. So that's why you're seeing it diverted this way. So sadly, as complicated as it is, you have a bow shock that changes and heats the not supersonic, but the solar wind or the interstellar wind that's moving too fast and can't get out of the way. It heats it, makes it warmer in what's called this interstellar sheath, bends it out of the way. And then the same process is happening with our sun in the solar system. The termination shock basically changes the solar wind as we know it, heats it up, slows it down so it can be diverted into the heliotail so that everything can just kind of flow around this whole obstacle. So we've got two different shocks working on two different plasmas, and we have two different sheaths. Basically, we call them sheaths because they're plasma that has been shocked. They're not pristine. So the only pristine stuff is the interstellar pristine stuff here in dark blue, and the green pristine stuff, which is the solar wind here. Okay, everything else, the light green and the light blue, that's all shocked stuff. That's where the Voyagers are. That's why we don't think anything. We don't think the Voyagers are out yet in blue. I mean, there's argument as to whether or not they are in the pristine blue or if they're just in the light blue. But this is why we really don't have, I mean, if our probes are still suffering with this, we're not completely out of the realm of understanding what our own solar system influence is like, let alone trying to understand pristine interstellar space, to understand what that system, what kind of effects it will have on anything else, or even understanding what it looks like. But hopefully this gives you an idea of how complicated this process is. And yet, we managed to have cosmic rays being affected by all of it. So you've got a breathing heliosphere that waxes and wanes, that the strength of that bubble moves in and out. Then you've got shocked plasmas that then cause this big heliotail down the backside of it. And then you've got this interstellar wind that's coming in, getting shocked. And it's only moving at like 25 kilometers a second, we think, something like that. And it's then having to be shocked and deflected around. Meanwhile, you've got these very energetic particles coming from all over the place trying to get in. Sound easy? Sound like an easy thing to solve? Easy problem? No, I don't think so. I'm so glad I do what I do and I don't, try to solve problems like that, especially when we don't really have any measurements out that far in situ, just the Voyagers. So we've got a long way to go before we understand the coupling between our sun's heliosphere, our sun's magnetic shield, and what lies beyond it. Okay, it's going to be a long time before we get that. However, what we do know, I see how complicated this all is. I'm glad you're getting a feel for it. It still confuses me. And I have no hope of actually trying to decouple it. And I wouldn't want to. I would not want to be someone who works at the termination shocks. I know people who do, and they can have it because it's a very painful process. So, the heliosphere, here is a plot showing cosmic rays. We've got cosmic rays from 1930 on to 2010. You can see we actually, back in the early 30s and 40s up to the 50s or so before the space age hit, we have the blue, we have ionization chambers. This is what we measured at Earth, where we were looking at cosmic ray showers. That's how the ray showers actually did have rays like gamma rays and X-rays and things like that. That's how cosmic rays got their name. It was because they were first detected here at Earth. We didn't know that the primary source of them were actually protons, but we do know. So once we got the neutron monitors in, we got much better data. But as you can see, if you look at the solar cycle numbers, the sunspot numbers, you can see when the solar cycle peaks, that's when you get a low, like look at 1960 here. You can see that's when you get the lowest number of cosmic rays. Right, the cosmic ray flux is the lowest. The count rate is the lowest in these neutron monitors, for example. When you get to solar minimum, that's when you get a peak in the cosmic rays. Whoops, let me put my hand here. And vice versa. So they are anti-correlated. It's because when the sun is super active, that shield is very strong. When the sun and the dipole field goes away. So those pretty waffle cones that kind of entice those cosmic rays to come in like a nice funnel, it's gone. All it is this big jumbled mess, and the whole thing looks messy, right? The whole thing looks like kind of like the edge near the heliospheric current sheet. It's just a multipolar sun, and it's very stochastic, and there's no fun entry for cosmic rays. But during solar minimum, you get those pretty waffle cones near the poles again, magnetically, right? And they just entice those cosmic rays to come in. But there is one other thing that you might notice. Notice that every other cycle, especially let's look at the cosmic ray flux here with neutron monitors. Notice the cycle's a little bit higher peak here. And notice this one's flat topped. And then this one has a sharp peak. And this one is flat topped. And the sharp peaks actually peak higher than the flat tops do. What's happening? Anybody know? The magnetic field of the sun is reversing, right? Every other cycle, it reverses to the same polarity. So if the sun is north here, the northward field is in the north, pointing out. Then the next cycle, the north hemisphere is actually pointing south. And then it points north again, and then it points south again. Notice that when the sun has its field pointing in the same polarity, with the same polarity, the cycles look the same. You get the flat top when it's southern polarity. You get the sharp peaks when it's northern polarity. Interesting, right? We call those A positive, A greater than 0, and A less than 0 cycles. And I guess I could show that right now. I'll go back to that other one in a second. And this is an A greater than 0 cycle, okay? And we'll talk about I'll go back to what the implications are in just a sec. But this is what solar cycle 25 is going to be, okay, or is. Okay, north is in the northern hemisphere, south in the southern hemisphere. North is positive. The magnetic field lines will look like this. Okay, so those of you who like to look at N as positive and they like letters, those of you who like to look at pluses and minuses, these two are equivalent. You can even take a look at the magnetic field lines. And I know this answers Mike Richardson. Hopefully, Mike, you're paying attention and not having to moderate too much, because this plot is for you. This is exactly what you had asked me to put up, so I have. So this is going to be our magnetic polarity. This is the direction that we're going. This is an A greater than 0 cycle, meaning it's a north-south cycle, and this is the polarity direction. And what that is that means it will have an implication for the GCR flux. And during our upcoming solar minimum, the GCR flux will be in one of those cycles that has the peak that is much higher, okay? And it means that we could break records once again. And let me show you what I mean by that. You probably can't, you may not be able to read this very well. Well, you won't be able to read it at all, but here's that bubble again that we talked about. There's where the solar wind, pristine solar wind is, right? Here's the termination shock is at the edge of that bubble. Here's the heliotail, right? So now you guys should all be experts on what the heliotail is. Here's the bow shock of the overlying bow shock from the interstellar wind. Everybody knows there's two shocks. Everybody understands there's two winds now, the solar wind going out, the interstellar wind coming in, right? The interstellar wind coming in. And there's where Voyager 1 and 2 have penetrated outward. Now, during the solar minimum, back in 2008, we had only up until then measured cosmic rays up to a certain level. Okay, we had seen how high cosmic rays were. When we went into that deep solar minimum around 2008, the cosmic rays shocked us. They broke the space age record. And it actually scared us a bit because we thought, oh my gosh, the cosmic rays are actually, almost 30% higher than what we anticipated, than we'd ever seen before. And that has implications for high altitude airline flights, right? For people, especially over polar passes. But once we got through that, we started having cosmic rays go back down. And here is a much better plot from that point. Let's see. Yes, this is about the peak of that solar cycle back in 2008 to 2010. You can see that's the peak right there. Okay. Now, the interesting thing, and this is actually from a paper from Mark Looper et al. This is the LRO instrument. This is Crater, rather. This is a lunar reconnaissance orbiter cosmic ray flux at the moon. And it's a very sensitive instrument. But as you can see, there's the peak where it was for solar cycle the end of solar cycle 23, that solar minimum, moving into solar cycle 24. You can see the cosmic ray flux began to drop for both helium and protons. Protons are much, well, I don't want to say, typically protons are much higher fluxes than helium, but in this case, they're looking at, they've normalized things. So, so it's relative flux, so they've normalized it. So I don't want to confuse you by showing that the helium line is higher than the protons. That doesn't mean there's more helium than protons. That's not true. This is just relative. So that's because of what he's doing in his paper. But notice that they both minimize. This was when the peak of solar cycle 24 was. And then as we move into the minimum that we are currently in now, look where we are. Notice how close the difference is. Okay. In fact, Mark Looper told me that at the edge of this, if I can get my hand to the right place, the edge of this, even though here on this plot, it isn't updated because you can see it only goes to January 2019, we have surpassed this. As a matter of fact, we actually have peaked at a higher level than we did in the prior solar cycle. So we have broken the space age record yet again. We are now more than 30% higher than we've ever seen. And just like we were a cycle ago. And here's the interesting thing. This cycle was an A greater than 0 cycle, meaning that was when the cosmic ray flux peaks the most. The cycle we're just finishing, was an A less than 0 cycle, meaning it was flat topped and not as high. The reason for this, the reason why the cosmic rays seem to penetrate A greater than cycles more than A less than 0 cycles, is because of the magnetic field orientation of our star, the polarity, so the magnetic field, relative to the intergalactic magnetic field direction. Cosmic rays stream much better into our heliosphere when the magnetic field orientation is like this. Our last solar minimum, the field orientation was the opposite. Now, when we get to solar minimum, our field orientation, when we get to it again, our field orientation will look like this, which is an A greater than 0 cycle. So if we have yet another low activity cycle, okay, and let's say Macintosh et al. Is wrong, if we have another low activity cycle, we could very easily break the cosmic ray flux records even again. So we will have even higher cosmic ray flux in another 10 years than we've ever seen during the space age. And that will have another massive impact on aviation, especially with the polar routes. So everybody be aware of that. Okay, that's the consequence of the A greater than 0 cycle. So, and then this is the last couple plots here. We're almost done. When Voyager, what we don't understand, of course, is, as I've hopefully been able to make clear, as we get out to the edge of our heliosphere, it'd be really great to understand what the magnetic field of that interstellar medium is, right? What is our galactic, what is the Milky Way's galactic magnetic field signature? Well, as I've already talked about, you can't look at it, magnetic fields, through integrated measurements. Faraday rotation is showing some level of promise, but it's really hard to make it work right. You have to really, observations have to be just perfect. And even then it's very, very, very complicated. I have Dr. Liz Jensen, who I went to grad school with, was doing Faraday rotation. Oh my gosh, it was insane. I admire her ability to stick through it because the mathematics involved is just massively intense. And the errors are sadly big. But they can show the way Faraday rotation works. It ends up allowing you to see how a field vector might rotate. The magnetic field rotates, and it gives you different signatures as something passes over you. So we have a hope with Faraday rotation, but we're not there yet. So we really can't directly probe the magnetic field of the intergalactic, interstellar medium, the ISM, what they say, the LISM, LISM is what they oftentimes call it, local interstellar medium. But we do have one trick, and it's called energetic neutral atoms. And what energetic neutral atoms are basically cosmic rays that, as they pass through all that junk, right, at our heliosphere, at the heliopause, and where all the bow shock and all that stuff was occurring, right, where all that complication was occurring, sometimes those cosmic rays end up hitting a proton or hitting another ion, and they do charge exchange. And suddenly that cosmic ray that was a proton suddenly becomes neutral. And so you can get suddenly a neutral atom that no longer sees magnetic field or electric field because it's neutral, but it still has the energy of the cosmic ray, and it has the vector, the direction of its origin. So it's coming in and it becomes neutral, and then suddenly at that point that it becomes neutral, it then just continues flying straight and it doesn't change. And so you can backtrack where that thing came from. And that's one of the neat things with IBEX, is that they've been able to, with IBEX, which is actually Earth orbiting, I believe, IBEX has been able to map these energetic neutral atoms that were once cosmic rays coming in from the interstellar medium. And what IBEX has found has been fascinating. And see if I can stand in the right place. Yeah. This is the map that IBEX has created. And notice this ribbon across this, this is an interesting, I forget the kind of, what do they call this particular strange map of the, it's basically the whole sky. It's a certain style of map, and I forget what it's called. I think it starts with an M, but I forget what it's called. And you'll see it in a second. I'll have it mapped onto the heliopause in just a moment so you can see a better view of it. But in IBEX's view, look at this interesting ribbon of higher fluxes. Okay, so these are energetic neutral atoms coming at a very specific angle. Now remember, these were cosmic rays before they became neutral. They became neutral right at the edge of our heliosphere. But before that, they were cosmic rays, and they were following a very specific magnetic field direction, right? And so when they become neutral and they have this very thin ribbon and they come from obviously a very specific direction, we know that this is the magnetic field of the interstellar medium acting on them and causing them to become aligned. And it gives us hints to what the orientation of our interstellar medium is magnetically. And when we map it onto the heliopause, right? So remember, that's the heliotail, okay? And this is the direction of our solar system, our sun's magnetic shield moving into the interstellar medium, okay? That interstellar medium is blowing this way against us, okay? And you can see the field lines moving out, moving around, the flow lines. This is what we're seeing. The ribbon almost is like a smiley face. Isn't that funny? But that is showing us hints, and we don't really understand it completely yet, but it's showing us hints at what the interstellar magnetic field is. And it's going to give us more hints as to how these cosmic rays get in and how these cosmic rays are being ordered by this interstellar magnetic field. And so it's beginning to give us an idea of maybe how the magnetic field of the interstellar medium, as you can see here, is going to couple in to the magnetic field of our own solar system to create a super system. Isn't that cool? So we don't know much about it yet, but just so you know, we are doing this kind of beginning to reach out into this realm and trying to put the whole picture together. Now, granted, it's far less space weather at this point and far more astrophysics, but it is showing a coupling of space weather and our sun's influence coupled into the much larger picture of the Milky Way galaxy. So, and I think that's it, guys. I think that's all I've got. Yeah. So that's the end. That's the end of the course today. And I'm sorry, but I probably only have about 10 or 15 minutes because I have to actually give the studio up to my husband. So I'm not going to be able to take, I usually do like a whole hour of questions afterwards. So I may do a Q&A later that's just a Q&A to catch up with some extra questions before I move into working on the Earth system. I know that's the next thing everybody wants me to work on and go into is what are the effects at Earth and how does the Earth's magnetic shield affect space weather as it enters. You can see how dramatically complicated the sun's magnetic field gets at the edge of the solar system, the edge of its magnetic shield. So you can imagine the Earth, how radically different space weather is inside Earth shield rather than outside just being delivered by the sun. It's definitely a totally different ballgame once you get inside the Earth shield. So that'll be fun next. But hopefully everybody enjoyed this class today. We finally got through the breathing heliosphere aspect. So I will definitely take questions if you guys have any. Let's see, what do we see? Thanks for sharing. You are awesome. You're so welcome. Thanks, great show. You're so welcome. What's your opinion on the electric universe? Oh goodness. I think, you know, the electric universe tries to fight so hard to say that the electric fields are the only things that matter, and you know they don't. Electricity and magnetism, they're coupled, and you really have to pay attention to both of them. So I think they push too hard one direction and they only are looking at half of the picture. So there's some good and there's some bad. I like the fact that they're trying to couple terrestrial weather with space weather, but sometimes they don't go about it quite the right way to get much traction with the mainstream science, and that's sad. But we'll get there. We'll get there. Thanks, Jeff. Really good. Thank you. Came in the middle. I did get through it. It's been an hour and 10 minutes, and I'm there. Yeah. I know these courses, I only do them once a month. So I try to give everybody, you know, essentially a whole month worth of classes in one go, because I just can't do it once every week. But I want to make sure everybody gets it. So it's always meant to be taken in parts. You're never meant to have to sit through the whole thing at one time. That's why I have like breaks. Like this time was split into two, right? I did solar cycle and then I had the breathing heliosphere. So take the solar cycle part in one go and then the breathing heliosphere in the other go. And it ends up being two really nice courses. So. Oh, you're welcome. Thank you. So awesome. Awesomus Maximus. Thank you so much. Thank you, Daniel. I appreciate it, guys. Great mini course. Good. I'm so glad you like it. As always, fantastic. Thank you, Chris. You're welcome. And I'm getting less questions this time. Oh, my goodness. Can Voyager go beyond the outer field? Sure it can. And we're hoping it will. Our issue is the power, you know, because it has an RPG. It's a radioactive generator. And it's dying, so we have to be careful. And then also how long it takes for the transmission to reach us. You know, we have to really keep watching, but we're going to watch it as far as we can until we lose the signal. So yes, we'll keep watching, and we're hoping it's going to get out into the pristine heliospheric medium soon. I mean, pristine interstellar medium soon. I'm not used to saying that very much. Okay, let's see. Quantum consciousness. Do you believe we can affect celestial events? Oh my goodness, that is way beyond my pay grade to answer. I would love for that to be possible, but I have no earthly clue about the answer to that. That would be a totally different conversation we'd have to have offline. Definitely not for this class. Oh, thank you, Jerry. I appreciate you putting a link to the other courses. Solar indices on ionospheric propagation. Infodog, I'm not sure what you mean by that. Take your vitamin D. Yes, absolutely. COVID. Oh, good. Thanks, Deepak. I'm so glad you enjoyed it. That's wonderful, especially the galactic cosmic rays. Yeah, and it's becoming more important. The galactic cosmic rays are huge, are a huge issue now. We even have medical industry trying to make radiation hard their components for things like ICAs, like inner cardiac devices, ICDs rather. The inner cardiac devices like pacemakers and whatnot. And it's going to continue to become even more critical as time goes on, because especially if cosmic rays continue to increase, which they very much, they very well may. So we shall see. When the solar winds stack up in heat, do they produce any light? No, probably not. They're so vacuous at that point that it's more of the fields interacting. So it's as much as we have these different regimes and we can plot them and make them look like they're, really big, intense things, we're really dealing with very tenuous plasmas. Most people believe this stuff, it's a vacuum, right? Space is a vacuum. So a lot of people don't even believe that there's really any influence at all. So remember back in the 50s and 60s, we didn't even know there was a solar wind. We thought it was all vacuous at that time. So not enough to produce any light, at least not maybe radio waves. Definitely light from that point of view, kilometric radiation, sure. So that is light. It's just not visible. It's not high enough energy. So I guess I need to be careful when I say that. Yes, it does produce light. It's just really low energy light that we would pick up with a radio antenna, not light we would pick up with our eyes. So hopefully that answers that question. Do you think the solar cycle could cause blackouts? I think not the solar cycle, but the events that could come from it, yes. Could we get another Carrington class event? Yeah, we had essentially 3 in the last cycle, and one of them clipped us. The other 2 missed us. Could we get another Carrington class event? Sure, sure. Do I think it's going to be the doom and gloom that everybody talks about? No, I don't. I think we'll be able to mitigate through. I also think that this space weather community is so savvy now that we will help educate people to maybe do things like reduce power consumption. I think there will be some of us who will be able to get on the news and educate the weather people so that they make intelligent, they talk about the solar storm in a very intelligent manner. And I think we can reduce the risk for overloads in our electric grids. Absolutely we can. It's just everybody knows what a rolling blackout is. Everybody knows when they have to reduce their power consumption. So I think that's something that is very doable. And I think we will see something like this type of mitigation, this massive public mitigation in our lifetimes. Absolutely. So that's what I'm working towards, guys. That's what we're all working towards, right? We're trying to get space weather on the map as a real weather consideration, so that we all can, go to Mars and do asteroid mining and be space tourists and not have it bite us in the butt, right? We want to be savvy about this stuff and not have it take us back to the dark ages. We want to keep moving forward. So, oh, good, Jerry. I'm so glad everybody was well behaved. Yeah, and yes, and I appreciate it too. So everybody, Jerry and Michael, thank you both so much for being moderators, and everyone else, thank you for all the wonderful comments. You guys have been just fantastic today. What can jets get from black holes? What can jets from black holes do to our solar system? No earthly clue. It's totally the wrong expertise. So sorry about that. And I think all of that will be skeptical. I'm not skeptical, but speculation, because I'm not sure we know that yet. Space weather is growing, and I love it. Yes, Mandy, I agree with you. I'm so pleased to see that it growing. It's honestly, it's time we jump into the 21st century. I mean, the 21st century got here, and we haven't moved into it yet. So it's time we all embrace it, and space weather is definitely a part of that. So rebuild the power grid. It's coming. It's coming. Weird radio blackout around noon today. I haven't looked at the sun today, so I'll be interested to see if there was any noise on the bands. Maybe we're having a little some C-class flares or something. There's not been a lot going on with the sun recently, so it'd be nice to see a little bit more activity. Debris from beyond the sun creates the blast we see. Debris from beyond the sun. I don't think I quite understand that. Sorry about that. That's very vague. You're welcome, Kim. I'm very happy to take the time to share. And thank you to my Patreon community, because they make all these courses possible. They also help choose the content. So if you're if you want to get your voice heard when it comes to the content, please join my Patreon community, and your voice will be heard, definitely. Okay. Yes. Thank you, Werewolf. Don't forget to like, share, and subscribe. You're so kind. That's so kind, guys. I know I'm terrible about that. I need to promote my stuff more, but I just don't, do I? I'm horrible. Do I think space weather has an effect on the geological events of Earth? Yeah, most likely. The problem is that we don't really understand the main driver. And I've said this many times before. The primary drivers are what we have to solve first as a mainstream science before we then can quantify the other drivers. It's like having the dirty water in the bathtub and the kids' toys underneath. They're all submerged. You can't see them until you drain the bath water. And then those toys are, they appear, and then you can quantify what they are. You can tell what they are. Prior to that, you're just kind of, speculating. So that's the biggest problem that's holding that side of meteorology back, is that we don't really understand quantitatively and can't predict quantitatively the primary drivers of things like earthquakes and other geological activity. Once we do that, we'll be able to understand tidal forces and the impact of tidal forces and the impact of space weather and all these tertiary and subsequent effects. So I think that's what's holding mainstream science back. It's not that they don't believe that these things are possible. It's just we can't quantify it yet. So there's a lot lower hanging fruit that they go after than this. Hey, babe, you ready?
Close, yeah.
Oh, yeah, I'm just doing questions.
Okay,
yeah, so
they
they
like
know.
10 minutes away.
Yeah, no worries. You're ready. We're just going to go on. Let's see. Okay. So be careful what you buy for your kids. Yeah, most plastic is toxic. No kidding. My goodness. Okay, I think that's it, guys. I'm seeing. Oh, thanks, Jerry. I appreciate you putting the link in the chat. Oh, mid-B flare earlier today. Yeah, mid-Bs can cause a little bit of noise on the bands. It shouldn't be too bad. Obviously, if you're on the day side, that's the only time you'll have a radio blackout or any type of noise on the bands from the sun. If you're on the night side of Earth, you're not going to, if you can't see the sun, you can't hear it scream, so it won't bother you. Nova, oh, thank you. Let's enter the 21st century with cosmic space weather. I agree, absolutely. That would be fantastic. Okay, guys, I think that's it. And my husband is now kind of freaking out, so I've got to give him the stage so he can teach comedy, improv comedy. That's what he does for a living. So wonderful, Daniel. Oh, Andy, all you guys, Dave, thanks so much for joining in. It's been wonderful, and I appreciate it very much. And I will see you all in a month. Okay? Take care. Bye.